trying to correct that from last night's email. That was too much bad traffic. What's healthier is looking what a stick. Okay. I thought I think of someone else, but a pleasure to meet you again.
It'll get fixed. And I'm like, oh, that's a good idea.
Sue, you have to do it with more gusto. Wake these people up. The coffee's not enough. Good morning, everyone. Welcome to another session workshop. We're going to get underway. First of all, we would like to thank our sponsors, ICANN, VeriSign, Nominum, Salesforce, Netflix, Network Utility Force, NZ and ZRS, and Power DNS. Just a few logistical announcements, and then I'll hand it over to Dwayne. Just a reminder for some of you, you weren't here because you're non-members. Now that you're here, in case there is a fire alarm or sounds of fire, there are 2 escape exits this way and that way. The closest one to us is this side where the escalators are. They'll probably be shut off, in which case you have to walk down. The alternative is there's a stairwell beside the escalators on its far side. Walk down, go past the Starbucks onto Ross Street, and we're told you collect there for muster. Another announcement I have, if there is any likely event, a medical emergency, please contact Dinesh or Sue, who will coordinate. They're at the back or just outside at the registration desk. And finally, just a reminder, have your badges, because you'll need them to enter the lunchroom, which is just outside the door to the next ballroom on the left. And with that, I'm going to hand it off to Dwayne to conduct this morning's session. Thanks.
All right, thanks, William. So another reminder, we have the PGP key signing, which will take place around lunchtime today. It's my understanding that the lightning talk submissions are now closed, and those have been selected or will soon be selected by the program committee. And we'll get started with the talks this morning. We have 3 talks up that are about data analysis. And our first one is from Elson Oliveira from CIRA, talking about using PCAP files in Hadoop file system, I believe.
Morning, everyone. My name is Elson. I'm part of CIRA's development team. And yes, today we're going to talk about a little bit about PCAP and big data and just a little bit of what we're doing and all of this. So first off, even though this is my first Dns Oarc, CIRA has been present a little bit in the past editions, but I added here just a quick overview and a little update of the new projects that we have. So we are the CCTLD for Canada. We manage a little bit over 2.5 million domains under .ca. And just a while ago, that was about it for CIRA. But we've grown, and we added some new projects. And first one being CIRA Labs. We launched this year, and this is where, as the name suggests, we try out new stuff, new technology. We have DZone. This is our secondary solution for DNS. Fury is our multi-tenancy registry platform. In fact, we just went live 5 days ago, so we are now officially a multi-service registry backend provider. And IPT is our internet performance test. Even though it has this name, it's not only about performance. We actually have a detailed snapshot of the entire Canadian internet infrastructure. And okay, so let's get started about this whole PCAP thing. Apparently, it's something that a lot of people are doing out there, and for sure it works. And just a little bit of why CIRA is doing that. What do we want? Why are we storing all of this PCAPs? What do we want to accomplish with that? So first off, in our DZone system, which is just turned 2 years old right now this month, but since its first release, we already have had some reporting page for giving some information to our customer in terms of queries and all that stuff, but it was really limited. All we had was just total queries, and it was being made in a half-hour interval. So, of course, we were losing essentially a bunch of data. If you think about all the information you have in queries and response packets and all that stuff, and we're only storing data for the total of queries in a half-an-hour interval, that's definitely not a lot. So we wanted to improve that. And the way we're doing it, we're just using those bind endpoints and retrieving JSON and saving, doing the difference in delta for the total query, so that was definitely not ideal. In terms of scalability, we were saving in Postgres, and we all know that that does not scale just because it's a relational database. So we want to just have more information that we could display to our customers. So this is actually a first refactoring of our DZone traffic page already with the new engine that we built. So this is what we wanted. Instead of just total queries, we wanted to be able to drill down to the query. So if you're saving all the information about queries and response, we wanted to give that ability through our portal to the users to be able to not only have the total queries, but go down to the actual query and response for a given server at a given time, and have everything in a per second level rather than just half-hour interval. So we went out there and did some research in terms of our options, and as usual we have thousands of options to get in the same goal. So we tried a few different options. We tried passive DNS, DNS tab, tool called Bro, it's a network security monitor, and vertical for the storage part. And everything came down to performance. All of this, it actually worked fine, but at a certain point, it just didn't scale. The performance was not being so great. And of course, it's not in here, but we also tried the built-in login for bind. And same thing, it's quick and easy to turn it on. It works nice, but it just doesn't scale. So this was actually our main issue. And we finally decided to use the Entrada toolkit, which we saw the presentation of some guys from SIDN who did a great job here. And we just decided to give it a try, and it's the whole PCAP HDFS thing with Parquet and Impala on top of it to do the queries. And that was essentially our starting point, and we took it from there because we knew that our main goal, our main issue would be solved with this, which it was to have a close to zero side effect in our main goal, which is like serving queries, right? We don't want to impact that just to do some traffic page. So in terms of PCAP, it was pretty straightforward. We had icon job, TCP dump, and that generates our PCAP. It was pretty straightforward, but the first thing we really needed to develop was our ingestion engine. So we had a few challenges, a couple of requirements. The first thing, we're talking about PCAP files, so of course we need to have the ability to read a certain amount of files, because it's an Anycast. We have over 20 servers, so it's a lot of files. We've got to be able to read those, of course. If it's PCAP, we don't get query and response all together. We see the query coming in, and a little bit after we have the response, so we've got to do the job of manually join them together. And since they're going to be displaying all this information to our customer, we need to overlay that information with our own information so that we can link each zone, each domain with the given customer. And we also did some other things, such as geolocating the IPs, just to have a better idea of where the queries are coming from and all that stuff. And because all of those are sort of expensive operations, we needed a solution that it needed to be parallel, async, right? We already knew that this did not work if it would be able to be a sequential and blocking operations. So this was like a hard requirement for us. And also using some in-house knowledge that we already have for some other DZone solutions that we've done in the past. We thought of using the actor model just for the simplicity of it and like the separation. We'd have like specialized task actors with very basic tasks for each one of them. And we decided to use a chain architecture. We're going to see just a little bit more details on that. So this is our toolkit that we use. It's a bunch of different technologies for each specific task. So as I mentioned, starting with the PCAP decoder, we did start using the RIPE decoder first, but we ran through some performance issues and some duplicated TCP packets. And so after changing to the Entrada one built by SIDN, just worked great, so we kept with that. The storage part, just using Hadoop with the Cloudera distribution. we have a staging table that, because we decided to use Flume instead of Kite, we're doing the first part that we write. We use the Avro data model so that we can just stream it through Flume. Then after that, after one day the data sits there, we do the conversion to Parquet. So Parquet, it's a columnar format, so it's very, very performatic because it just stores everything from a column. So the data, they tend to be similar from one column to another. So it's just easier to read and faster. So, and we also tweak the size so that it matches with the underlying file format. So we are currently doing 256 meg. And after that's saved in terms of retrieving it, we're just using the Impala query engine. It's just a layer that sits on top of the MapReduce. And it's after everything set up, it's just SQL, so it's pretty easy and straightforward to use. We don't need any extra knowledge for that. So if a developer comes in and everything is all set, he's just going to be doing SQL, and it already uses all of the data nodes to do the retrieval all in a distributed way. So we're using JDBC for ingestion engine just because we're doing it in Java, and Impala for the Python project that we have. And we also do some aggregations. For that, we have some jobs that we schedule using Uzi, and for converting that into some tables in our Postgre database, we use Scoop, so we have daily and monthly aggregations. All right, so a little bit more about the actor chain. So as I said, got to do the processing concurrently, and one of the requirements that we had was just to have the ability of configure the number of instances of the chain, because since it's an Anycast cloud, we can be adding servers whenever we need. So we need that ability to scale without changing the code base. So we can just, with a config file, we can change the number of instances, and our power of processing is gonna increase. So it's all about performance. And how did we do that? Again, we used a little bit of knowledge that we already had from DZone. We used a framework called Akka. It's an open source toolkit for concurrent and distributed applications. So it runs on the JVM, even though it's written in Scala, but it has bindings for both Scala and Java. So it has the reactive flag, so it's all about responsive, elastic, and resilience. And yes, it supports multiple models, but we did focus on the actor model. Okay, this is a big picture of our ingestion engine. So everything starts on the top right with the servers receiving all the DNS queries. So we do port mirroring, so that we don't want to impact our servers in any way. So the port's mirrored. We do a TCP dump, and we just do an SCP to our ingestion engine. And in the top left, that's where our ingestion engine kicks in. If you see the first actor that we have there, it's outside of the chain, so it's a single instance actor. All it does is just receive a message with the name of the file, and that's it. So a new file comes in, this actor forwards a message to the chain. So the point of interest of the chain, you see there's a round robin box in there, so that means that this is the actual chain. So it's actually an actor router, so it means that it has one instance, but underneath it we have as many instances as we want. So the very first actor of the chain is the pickup processor. All it does is open the file, decode it, grab a query, or response, actually grab a packet, and sends forward. That's it. Doesn't care about anything else. So the second one, it's going to do the join. So it's going to take the query and try to join with its response. So we use a Guava cache here so that the packet sits there for a little bit, and we try to match them. And then we send it forward. That's our DZone overlay actor. That's where we go to our DZone database and try to match the queue name with our customer. So if we have a customer that owns that domain, so yes, we do care about it, we send forward. And again, we have a a cache here, but this is just a performance cache. Of course, we don't want to be hitting the database every single time we get a packet for that queue name. So we have a cache just for performance here. Next actor is just geolocation. So source IP, we try to geolocate it and move forward to the last actor of the chain, which is the actor that actually writes to the HDFS. And again, it uses Floam, so it's a stream manner instead of just actually have to open and closing connections. And so yeah, this finishes the chain. And as you can see in the bottom, we also use a Spring context just for creating the instances, because we're doing the cache here, some of the services, they're actually singleton, so that the multiple instances of the actors, they actually share the same cache, even though they do their processing on its own, but the cache is shared. So we've got two different scopes here. The first one that I mentioned, it's for DZone. This is up and running already. We have our traffic page ready, working with that. So it's the Anycast cloud with a little bit over 20 servers, and we get an average of 1,000 queries per second. For the PCAPs, we put two different limits if it's reached the size or an interval of 5 minutes. So we didn't want to files much bigger than 1 gig. So if it hits 1 gig before the 5 minutes, it's going to cut it, or if it reached the 5 minute. And the second scope is for .ca. That's more for the labs. We're still working on that engine. It's not up and running, but it's a bit bigger. We have an average of 10,000 queries per second, and it's going to be a cluster of 4 nodes, so it's a bit bigger. So we've got two different scopes here. All right, so we already have all the data that we didn't have before. So of course we can do a lot more. Here's just a quick example. All we're doing here is just plotting some dots with the source IP geolocation and just linking it to the destination server. That's it. And this is already cool for a dashboard or whatever we want to do it. We can actually start to find some weird behaviors. If we know we have a bunch of servers in Europe, and depending on the number of the queries that we see coming from there to North America, that could be something depending on the number of that. So we already can start tracing some different behaviors that we did not expect just by using the data as static as it is in there. But again, this is a lot of stuff that we're saving now. We just thought that we could do a bit more than just grabbing it and displaying it, right? So this is why we move forward a little bit and start playing with some machine learning techniques and try to understand a little bit more of what's going on with our servers, and just try to extract some more information and maybe stuff that we didn't really know just because we didn't have that before. So again, we went out there, did a bit of a search. There are millions of options in terms of applying machine learning, different frameworks, different languages, and lots of options. So we decided to give it a try with Python and a framework called sklearn. It has a bunch of abstractions. We can use the main algorithms out of the bat. It's all implemented, so it's pretty cool, and you can get into it kind of fast. So we started playing a little bit with the supervised learning at first. If you think about a weird DNS behavior, almost all of it we can, in a way, show that in a spike, right? Almost all of the weird behavior that we don't want, we can, depending on the way you grab the data, you slice and dice it, you can represent it into a spike in a graph. So the very first thing we did was just do a spike detection, right? We don't want to rely on somebody actually opening the graph and displaying it to detect. So we started with total queries and by location, per type, per source IP, basically by whatever we want. It's just a matter of how to grab the data and fit into our model. We also have non-responsive queries. And it's kind of weird, but we also get a bunch of non-asked queries. So every now and then we get a lot of queries that we just never asked. So that's been saved as well. And we can do a spike detection for that. And moving forward with the unsupervised learning, where we try to make, understand a little bit more of the data and actually learn stuff that we didn't really know just because we didn't know that pattern was there in a way. So we played a little bit with the k-means and dimension reduction, and I'm just going to show a few experiments that we did. So first thing, we need a predictive model, right? Machine learning is all about having a predictive model, and we have big data with a bunch of queries and responses, queue name, server location, geolocation, port, servers, and all that stuff. How do we convert that into a predictive model? How do you do that? So for our spike detection, first thing we needed was to actually extract some features and train the model. Like, what do we want it to be to detect, right? So we started very simple. We just took 2 features. So in the axis here, we have one feature is just the difference between a given value and its previous. And the feature 2 is just the difference between a given value and its average. So it takes into consideration all the values to the point 0, and it extracts 2 features. So we just played, here is the very same training data, but for different algorithms. So we see that the decision surface here, what we would get from this model, it's quite different. So this is a discrete classifier. We just have 3 options for a spike classification. We got like a regular traffic, so no spike at all. High traffic is just a small bump, and a high traffic would be a very high spike. So that's about it. 3 different classifications. So here's actually the result of this detector. And in real data, it's a small interval here, but we started to apply in real data. So as we can see, we do have some spikes. And usually in the first one, it's a red one, because the previous values were a bit low, so it's an extra spike. And if you see here, then it tends to get high, because the previous one was high already, so it gets yellow, and then it kind of treats that as a regular traffic because it's using the average. So the idea here is to have that spike, and if it keeps in that trend, it's actually considered normal. So here is a bit of the unsupervised experiments that we did. We were using k-means with a fixed number of cluster, and all they're doing is just plotting where you see here the blue axis. These are the centroids that are suggested by k-means, and the red dots are our actual server positions in the globe. And here we're just using geolocation. We're not doing BGP information. We're not plotting ASN or anything. It's just to get a little bit of the hang of it, and just to see what we can do. And it's kind of obvious that we have the axis here. It's in areas that obviously we don't have servers, so that where it'd be better suited for new servers. But again, we're not taking into consideration here BGP or anything else, but it's just to get the hang of it, or stuff that we could be doing with it. All right, and here we're using k-means as well, and a little bit of a PCA to do dimension reduction. It's a very simple model. We just have four features here, and we just did the reduction for displaying purposes. I didn't want to display in a 4-dimensional graph, so I just reduced it to 3 just to make it a little bit easier. But we can actually use that for more complex models to actually fit the model, and with the reduced dimensions. So what we have here is just 4 features: total queries, distinct servers that the queries came from, that they were sent, distinct sources are the actual source IP that they came from, and how many different R codes that we got for that given query. And that's it. That's all I used to fit in the model. And I just asked k-means to give me two different classifications. And it's kind of hard to see, but the dots that are a little bit farther away, they are in red, which means they got classified differently, of course, than the ones that are in the left. And that means that they are just outliers. They are different than the rest just because they are farther away. And that could mean something, right? And we have here just a list of the first 3. And as we can see, we have 3 different R codes for a given domain, and that's not ideal, right? If you have an Anycast, it should be all same answers for the same domain. So probably got a no error, server fail, or something different, but it should not happen that way. So that's probably what helped them to be classified as outliers. So just by grabbing those features, we were able to put the queries together and just find stuff. All right, so for future works in terms of the actual analytics, we can, as I said, just improve the use of the data that we already have. Just in terms of displaying, there's a lot to be done in terms of graph enhancement. And we can also lower the granularity of the search and use the filter that we have to the user. We can put whatever we want that has in the entire TCP packet. We can just filter by type, by whatever we want. In terms of actual research, we can of course move on with the experiments. We're just getting started. There's a lot of behaviors that we can detect and behaviors that we're not even quite sure yet of what's happening. So just do more experiments with that, and of course applying the existing ones that we already did, because it's not in production already. Those are just experiments. And in terms of the architecture, as I said, it's in production. It runs fine. It's all right, but we've got some ideas to make it better, because we are still doing SCPs, right? Generating PCAPs and TCP dump PCAP and SCP, and we have some ideas to maybe make that better and get rid of the whole PCAP and SCP file and just use a stream-like, more real-time to the ingestion engine, so that we don't have to cut PCAP file, do SCP, and all that stuff. And for the engine, even though we're already using NACA and the extra mod and all that stuff, we're still running it in a single box. And you got some ideas that in the future, if you want to scale it even more, to put one actor in a different in its single box. So instead of doing a local remote lookup for the actor, we just grab the actor from a different box, or just use a different queue or something, but just to make them work from a different box. That's the goal. Right. And right, I think we still got some times.
Yes. Thank you, Elson. We have some questions for Elson.
Sebastian Castro, CRS. I'm going to pick Roy's line. Very, very interesting presentation. Very, very nice. Is there a reason why are you using supervised learning to find these anomalies in traffic? Have you thought, for example, because yeah, I've investigated a little bit around how to detect anomalies in traffic, and you usually do it real time, and you treat the data as a time series. So you do sliding windows and stuff like that, not supervised learning, because you need to go and get the data, collect it, put it in a right format, and then train the model. And it's like too slow for the application. So I don't know if you have the chance to thought or investigate around real-time detection of anomalies.
Yeah, definitely. But the reason we did was just trying to detect something that we already knew. That's kind of the logic we used.
Okay.
And so we don't do the training on the fly. We just previously trained the model to detect the spike in the range that we want, and then we have a trained model, and we just use the data, which would be the real data, but we just query and just run the predictions, right? So we're not doing actual training afterwards.
Okay.
You know what I mean? So we train it, we tweak it the way we want. Once it's okay, then we just run predictions. That's for the spike detection.
Do you retrain the model?
Well, no, not right now. We just did a static training, and that's what I'm saying. Once we tweak it and it's good, well, this is spike, because spike is kind of subjective, right? Well, was it high enough? It was not. So we just tweak it. This is good. This is a high traffic, as we had the 3 classification. High traffic spike. It's kind of good for what we want, and then we just leave it like that, just to run predictions.
All right, great, thank you.
Christian Petras, DNIC, graduate of Oarc, thank you. But one question, do you process PCAPs to Apache Packet in the name server location and transport it to your data center, or what do you do? Because I talked with the guys from SIDN about this problem, and they told me, oh, maybe we should do it in the name server locations to have little packets.
We do transport, so we have what we call stats collectors.
Okay.
And we generate the TCP dump with the PCAP, then we do SCP.
Okay.
And then in the box, which we call like the actual ingestion engine, that's where we open, decode, and process, and do all the...
So you transport a big amount of data?
Yeah, PCAP. We transport PCAPs.
Okay.
Yeah, like
Okay.
as raw as it is.
Okay, so that was one problems we mentioned about because our amount of data is too big to transport it back to the data center.
Yeah, but like as I said, for us it's working fine so far.
Yeah.
But that's one of the next steps that we have like in the roadmap is kind of sort of try to get rid of the whole PCAP thing and
Yeah.
SCP. We don't want that anymore. So that we can do a stream kind of real time thing. That's the goal.
Okay, cool, thank you.
Hi, Roy Arends from ICANN. Just to repeat what Sebastian Castro said about me, yes, brilliant presentation. I have a comment, not specifically about this presentation. I see a lot of this effort going on in the last couple of years. Personally, I've been involved in this as well at a previous employer. I think, if I may speak freely about this, I think it would be a good thing if, for instance, in the next Dns Oarc meeting, which is either in Manchester or Budapest, if I'm not mistaken, to maybe have a showcase, a demo during lunch of all these different implementations. And I would love to have open source implementations, if that makes any sense. So that people are able to learn from each other. I love this stuff. I understand the problems you're trying to solve. As ICANN, when we move data around, we're trying to solve similar things. There's a team at ICANN busy with that. I hope that you will hear more about this afternoon, but we'll see. Yeah, I think I don't know how to properly request this. Maybe this is my official request to have this demo session at the next Dns Oarc session. Thank you.
Thank you. Yeah, it makes sense to have some space to get more detailed in this, and yeah, and about the open source, yes, like the foundation of the lab is not only to use open source technology, but also to produce and give it back as output, also open source. So yeah, it makes perfect sense. Thanks.
So I'm gonna cut the queue off. You guys are welcome to go, but after you, I'm gonna relay a question from Jabber, and then we need to move on to the next talk. So 3 more questions. Go ahead, Jabber.
Okay, so just a quick question. Do you worry about matching queries and responses that span different PCAP files?
Sorry, this Ben?
That are where the query is in one PCAP file and the response is in a different one?
Yes, we do. We consider this an edge case, like not to have, because the PCAP would have to be cut at the very same time, right, in between query and response. But yes, the cache that we have, we have a config time for that, so the packets actually sit there for just a little bit, enough so that we can grab the next PCAP. So if we got cut in between query and response, it should be.
And data aging?
Sorry?
How long do you keep data? Maybe I missed it. Do you discard data?
You mean the raw PCAP or?
Or processed?
It's for a year. That's the goal.
David Lawrence, I was just following up on the whole open source question. I was wondering, when I got up, it hadn't yet been addressed, but now that it has been a little, do you have a plan that you do intend to, or is this a conversation you still have to have internally, or?
Well, we still don't have like hard dates, but
Okay.
as I said, that's the plan. The
Okay.
Zero Labs, we just released a different project, open source now, and as I said, like that's the idea, not only to use it, but to output that as well. So that's the plan.
Okay, great, thank you.
Okay, so I've got a question from Jabber. So if you were to live stream the data, might that cause some network overhead and impact on the name server itself that would be undesirable? Or would you live stream from a port mirror? Or
for sure it could, and it's something we keep in mind, like not to happen to avoid, because as I said, okay, this is all cool, like data that we're gathering, stuff that we're finding about it, but our main first concern is still respond to queries. So we don't want to do anything that like put that in danger. And we're just not quite sure yet. That's R&D for the future, so we're going to do tests. But for sure, whatever we do, we're going to make sure that the queries doesn't have any impact.
All right. Thank you very much, Elson.
Thank you.
So next up is Ralph Weber from Nominum. I think this is going to be another interesting story about an exciting attack, yeah? Or at least an exciting event.
So I wasn't initially not planning on presenting anything this Dns Oarc, and then came August 3rd, and I was on a call with a customer who were presumably seeing an attack on his network. And we digged a bit into it, and it was an event as it wasn't an attack, and the domain that was causing all that problem was vd2go.com. So what is vd2go.com? It's a Western Digital personal cloud storage, so it's a device in your home that backs up your data and that you can access from the internet and have as your personal cloud. I mean, it's a nice thing to have, and it's normally not a problem, because when you look at what the DNS traffic on a normal day for this domain is, it's pretty benign, and, well, mix the slide here. Okay, so let's do, well, anyway. So the normal day operation is mostly AN quad A, and as you see, it looks like the service is actually working on IPv6, which is a good thing. The names that are asked are mostly www, and when you then go down in the chain, it looks there's some things like these relay things that are pretty often are appearing, and every device seems to have an ID, and that also gets asked, but even less. And if you look in the query types, there's some DNS, somebody's trying DNSSEC, the domain itself isn't DNSSEC signed. So it's nothing normally to worry about, and I'm not sure if you can see that. That is the DNS setup before the event, and it looks like they were making a move or were doing something, because the delegated names from the parent don't match what's on the child, and even the IP addresses that are on the child for the names that are in the parent don't match. So it looks like they are planning to have some move or something like that, and with that, they were actually sort of cutting the branch they are sitting on. And so when, so now we come to the actual traffic. The traffic normally is flat. So normally when you have traffic in ISP network, you have it's a curve. You have it starts up at 9 a.m. in the morning. It goes on up, and the peak usually for subscriber end subscriber traffic is around 9 p.m. This traffic is flat. I mean, we looked over it a couple of days. There really isn't much deviation between night and day. It's really a flat curve, and it's relatively low. So as I said, it's 0.002% up to 0.6%. So the amount of traffic, when you compare that to the likes of Google and Facebook, who are sometimes in the 2-digit range, it's really, really low. And the clients that are sending the traffic are also low. So about 0.5% maximum is what we saw of the clients in the network that actually did have these devices or were asking for these devices. I mean, if you have a cloud service, there's in and out, so it's not, the clients are not the actual people having the device, but the people are trying to access the devices. So as you see, it's an empty road. Normally nothing is happening for that domain. And then came August 3 around, and on this day, the name servers that were delegated with the clues became unavailable. They first became unresponsive or slower to respond, and then at some point they just didn't respond at all. Now, as long as you have the sort of stuff you learned from the child in your cache, you might actually still resolve some of this, but at one point you have to go back to the parent and ask, and at that point your resolution will fail because you're not going to the name server that is delegated. And the traffic pattern on that day was very spiky. I mean, I'll show you a graph soon. It was kind of a curve, and the relative QPS just for that domain, I mean, was 4% depending, I mean, there was a direct relationship between how much clients were on the network that had that traffic and the actual resulting traffic impact on the network. And up to the most we saw was 43% on a customer network of all the traffic they had was just for that domain. And that's more than Google and Facebook usually have combined in the day. Now, when you turn it down, though, you recognize the actual traffic that you see per client is relatively low. It's 3 to 20 QPS. And you think, is that really a problem? 3 to 20 QPS? Well, if you think about it, we have, when we size our software for subscriber networks, we say, if you have a subscriber, it's going to generate 0.2 QPS average over the day. So if you have 1 million subscribers, it's 200K QPS. And now only a few subscribers have more, 0.5%, and that's 5,000 clients. But if you then, these 5,000 clients do 20 QPS, you have 100K QPS, and that's half the traffic you see on a normal day. So a few clients can have a huge impact on a subscriber network. And these are some graphs we saw from some, we generate out of the traffic we saw from our customers. As you see, there are customers that were not affected that much. This graph, the normal traffic is R-code 0 traffic, so that's something that was okay. And the traffic below there is the westerndigital.go.com, which of course at that day was all serve fail. I mean, there were no good answers there. And you see it's up to the 40% we saw in traffic. And it was kind of, it started around 12 something, and then it went until the evening. All the timing here is UTC. So depending on where you were affected more or less, because if that occurs in the sort of night when you don't have low traffic, you probably don't care that much. But if that happens in your busy hour, then yeah, you do care and you might want to do something. When we look at the actual stuff that was asked during that day, and that's just during the incident, so that's from 12 to 23 in the day, so it's not counting the normal hours. And you see the www get much less popular, and the stuff that gets asked the most are these relays, so I would guess that they are shuffling data around and are trying not to access them. The devices were asked not that much, so it looks like more so the devices that they had tried to access and shove data off. And the other thing that was kind of quite remarkable, Quad A wasn't asked that much. I mean, if something goes south, it looks like it's all still IPv4. There were some other things asked. A6 really, I mean, I'm seeing this over and over again. I've given a couple of presentations about data we see, and then when I look at A6, I said, really? Some of the things never seem to die. So here a quick summary of the findings that we found. I mean, a medium-sized domain or even small-sized domain can cause a lot of strain on the infrastructure, and I mean, we still should over-provision our stuff, but maybe a lot of things that can happen we just cannot account for. And the other thing is 2 QPS, as I said, it's not much, but it still would be good if the people who write DNS client code, if they get a serve fail and they maybe get another serve fail, maybe just wait a couple of seconds before you ask again. That helps everybody. And the chances that you're getting a different answer the next second or the next millisecond are pretty slim. So, and I'll show you why also the getting the next answer is because one of the things that was interesting about that customer, he was migrating from another solution to our solution, and the impact of this event to the clusters where he was still running some 0.99 were less. So I was thinking, why is that? And that kind of made me thinking, well, maybe I should have a look at how different software responds to these events. And so I've thought, okay, let's set up a lab and replicate the event. Because the event in the end was a domain, or the name service of a domain not being reachable. And I created a lab setup with a couple of authoritative and one recursive servers, and then tried to figure out what is happening if I send lots of traffic to the recursive server for a domain that just serves fails. And I mean, I thought, okay, well, let's just ask the same name over and over again, because it probably doesn't matter anyway. So, and I wanted to have a timeout of 5 seconds, because that's what most clients still have. Anything that gets after 5 seconds is really irrelevant. And I said, well, 10,000 QPS, that probably was a bit on the low side, but I didn't want to stress these servers too much. And I want to make sure if you have worked with DNS perf before, the -Q 2.5 million means that actually, even after 20 seconds, it will keep on sending traffic, because the timeout has not been reached. So that's just how you make DNS perf send traffic even if it doesn't get responses. So the command is there, and if you want to replicate it, feel free. I then, on the caching server, installed a couple of different softwares. I would like to include Not, but I sort of couldn't get it compiled on CentOS. We're working on this, so we'll maybe have an answer on that next time. But this was the software I tried. Bind99 for asking one bad domain, 600,000 packets, 0 answers. What? Bind910, same thing. Tried Bind911, it became a bit better. It answered at least 50,000 packets, and then Cachev and PowerDNS seem to be around the same ratio. They lose some packets. Again, this is a use case where that normally never should occur. So it's okay probably if you lose some of the stuff. Unbound, again, around 10%. That looks really weird. I mean, I've never seen kind of servers not answering that much. So am I doing something wrong, or what actually are the details on this? So I made a graph. Of course, the 0 answers Bind99 and 910. I can't do anything because they're not answering. The graph will be flat. But for 911, it looks like after 10 seconds, roughly, it shoves back a number of answers, and then it waits another 10 seconds, and then again shoves back some answers. When you look at what the stuff that Cachev, our product, does, it waits for 2 or 3 seconds, and then shoves back lots of answers, and then again tries to resolve and wait some things, and then shoves back more answers. PowerDNS seems to wait for a second, then shove back more answers, and then it's flat. Interesting. Unbound waits for 30 seconds, then gives back some, then waits for another 20, 30 seconds. It looks really weird. It looks like also there's different server software has different personality. And the reason for that is I believe, first of all, how do you recurse, and at what point do you give up recursion? That's the first parameter that you have. And some software tries longer, some tries shorter. And the other thing is, I mean, serve fail, nearly up to these days, all of the software have some timer in there where they say, okay, if I got a serve fail for a domain, I'm going to cache it for a certain time. And the longer the timer is, it of course means less work. But the longer the timer is, it also means the recovery takes longer, because if you get a serve fail and cache that for a minute, then, well, if the domain becomes good again, you have to wait a minute for it to get back, which for machines probably they retry, but for persons might be a thing. And but the test that I did really didn't reflect what the westerndigital.com was, because we were seeing more names asked for the name server. There was a lot of subdomains. I mean, like 5,000 subdomains was what I kind of averaged per server, because the thing was also different depending on the client that sent the traffic. So I said, okay, I'm going to make a different test, and this time around, I'm going to ask it 5,000 different subdomains of that sort of of that non-domain that you can resolve. And then I'll fire the test again. So this time it looks a bit different. So everybody answers, but the level of answer is different. As I said, the older binds around half of the traffic, and that pretty much matches what we saw at that customer, where the impact was around half of what it was in our cluster. So that makes sense there now. I can explain that. And as I said, with bind 911, the latest version, it's the same as all the other servers. They are answering nearly all the packets. Unbound still doesn't answer only half, but so in the end, it's more consistent. You get some answers back if you ask the server a lot of stuff. And let's look at the details. So bind 9 seems to, 9.9 to be precise, seems to have a wavy. I mean, we saw with the 0 packets, we saw there was some spikes at the 10 seconds, which you sort of can also see still here. 9.10, roughly the same kind of traffic, and all the others, I mean, at the first second, you'll really try to figure out what the thing is, and then after you figure it out for that subdomain, it looks like you're caching the fact that the subdomain is, and the graph becomes flat, and that's it's a bit more spiky here. So we'll try harder maybe to get the traffic. And I mean, PowerDNS is the same. Waits for the first second and then kind of is flat. And unbound again, I'll guess the impact on an unbound cluster in real life would probably be the same, because it tries harder maybe at the beginning, but if this was an event that was going over 12 hours, so losing the first 25 seconds probably isn't too much of a hassle there. As I said, I didn't have the numbers for not, but well, maybe do them. So given enough traffic that serve fails, all of the servers will answer, and that will cause a lot of strain in your network, because it looks like the devices that are asking for these names are retrying and retrying and retrying and retrying. And that's the difference between, I'll guess, a machine and a human, and that makes me a bit of nervous when I think about the Internet of Things, because we will get lots and lots and lots and lots and more of these devices that are machines, and machines don't, I mean, a for loop is pretty easy to program, and it looks like these people that are doing this device are very good in doing for loops, so I would really urge people who are writing clients to maybe back off something, because if you have more and more and more Internet of Things devices, then something with these domains goes bad, and I mean, Murphy laws tell you everything will go bad at some point. It will have a huge impact on the infrastructure, and as I said, with this domain it was easy to get, because you could sort of easy spot it that subdomain, and the amount of actual subdomains, so the ratio from normal subdomains on a day to the subdomains on these attack days was the same, so it was okay. It's not a PRSD attack or something like that. That was easy to spot, but going forward, if people start also working with maybe multiple domains to doing this stuff, it might be actually be hard to spot that stuff. So that's it. Thank you. Now time for question.
Yeah, thanks, Ralph. We've got about 5 minutes for questions. I'm going to tentatively limit it to the three of you who just stood up.
So Paul Hoffman, this is actually a comment, not a question. One of the things when you're saying, oh, we hope that developers will, not do for loops like this. One of the most interesting things about this, I don't know if you followed it the day or two later, almost nobody uses that service that they are querying on. All of those queries are automatically generated whether the user has actually bought in their WD2Go or not. So this is actually being done for the customer who is actually not using that service. So it's not just oh, well, these customers, maybe we can get in touch with them. These are the machines doing it with no one wanting, or almost no one wanting that service.
Yeah, I mean, that's the thing of the IoT device. I mean, you have a device and you put in your home and it does something.
Right. And this is it checking, checking in, maybe trying to give you an ad or whatever. But this is not something that almost anyone asked for.
Hi, Robert Edmonds, Fastly. So you did this synthetic test. You showed all these slides for your lab setup. Did you also perhaps make an attempt to, find one of these devices in your store and, buy one and try to simulate the failure scenario?
No, I didn't.
Okay.
But it's an interesting idea.
I mean, I guess it's sometimes called junk hacking, but being able to verify if that's the mechanism that's occurring. You mentioned it's very easy to write a for loop, right? It's also very easy to write a loop that does a blocking DNS lookup. So, in your opinion, would it be better to send back a serve fail in 1 millisecond or 900 milliseconds? Would that?
I mean, there was this talk yesterday. I had a discussion with on the privacy where you actually might have an advantage on delaying responses. I'm just out of operational things and running servers with high QPS, delaying stuff in servers at will makes me feel nervous, because I can see how you can maybe abuse that and do that. So I think the recursive resolvers are there to give you an answer, and to give you an answer fast. The client, if it gets an answer, then maybe should say, okay, it's a serve fail. I'll maybe wait 1 or 2 seconds and then ask again. And if I still get a serve fail, I'll maybe wait for 5 or 10 seconds. So these backup strategies, I don't think implementing something in the resolver will help in the long term, because it might help in this use case, but there are tons of other use cases out there where it's actually worse if you give back the answer delayed. I mean, like storms, when recursive resolvers are overload, they are not giving back an answer in 5 seconds. And this means that most of the clients then, okay, try the other server or try both servers in parallel. And then you become these overloaded situations where it's kind of a huge spike because of the clients retry like crazy. And so usually it's better to give back an answer fast. In this case, it would have better been to drop it or give it back later, but I don't think that putting that in the recursive resolver helps us in the long term.
Okay, thanks.
David Lawrence, you probably are not actually even the best person to ask this question, but I haven't noticed Mark or Evan around today. Do you have any insight into why 9/11 actually addressed this? Was it like deliberately they realized, oh, hey, look, we have a problem here?
So before I did the actual synthetic test last weekend, and I sent email to Mark, Evan, Wouter, Bert, and all the authors of the service. Bert answered that he's kind of, his normal time is 60 seconds for serve fail caching. That explains the power DNS graph. I haven't heard back from Wouter, Evan, or Mark yet, so I don't know.
Okay.
No, there's a guy that maybe has an answer.
Yeah. I'll address it.
Hey, Eddie Winstead, ISC. So we did some things to do exactly what you're talking about. Fetches per zone, fetches per server in 9.10, but they're not owned by default. They are owned by default in 9.11, and I think that's why your graphs are different. There's also some server fail caching that wasn't on default in 9.10 that is in 9.11.
Yeah, and I said with modern servers, I mean, the output seems to be the same after 30 seconds. So.
Thank you very much, Ralph. This was great. So our third data analysis presentation is from Sebastian, who's searching for resolvers, I believe.
Good morning. Yeah, I'm testing this microphone. I was yelling yesterday. Well, good morning. It's a Saturday morning. We're all asleep, and I'm between you and coffee, and well, actually, not coffee. So I'll try to make this quick, nice, and easy. This presentation is about searching for patterns in DNS authoritative data in order to find resolvers, so source addresses that represent a resolver. This is a joint effort between Jing Kiao, which is one of our new additions of the R&D team, and myself, and we are from NZRS, NZ, New Zealand. So, in case you haven't heard about this, we are working in what we call the domain popularity ranking, which is an algorithm to derive the popularity of a domain name from authoritative data. So if you're a CCTLD, you can go and calculate a ranking of popular domain names from the traffic you see in your name servers. We're trying to mine that data. However, if you have the chance to actually play around with DNS data at any level, you will find out it's very noisy and there is a lot of rubbish there. So Ralph just reported we saw this big spike and we didn't know what happened. And they have the resolver data, which is more granular, so they see more stuff. So one of the cleaning up we're doing on this algorithm is try to find or determine which source addresses represent what kind of functionality in the DNS. So we did some work on this at Keira like 7 years ago on trying to find monitoring hosts and resolvers and some other sources. And we decided to go and pick that idea and develop a little bit more. So what we're trying to answer is, from the authoritative DNS data we have, can we go and pinpoint the resolvers? So DNS data is noisy. We have a very long tail of addresses sending just a few queries on any given day. So we pick a few days in March. And from this CDF plot, you can see like 60% of the traffic is represented by just the first 1,000 addresses. And if you go to the 10,000, you get roughly 80% of the traffic, so it's a long tail. So we identified 686,000 unique source addresses in a day, and roughly like 650,000 of them represent just the very long tail. So you will see a source address sending one query one day, or maybe another query another day. So there is a lot of like very spontaneous DNS clients going to an authoritative. And this is the same for the root zone. Dwayne have done this analysis many times, and some other of you CCTLDs have done this before, so we all more or less know this. So in order to identify the resolvers, we need some data, some curated, good quality data. So what we did is we talked to the local ISP, so the traffic we have is heavily New Zealand based. We talked to the local ISPs and asked them, which are your outgoing source addresses for DNS traffic? Because some ISPs have more than one resolver in different cities, so they have different architectures depending on the size of the ISP. So we asked them, can you give us the source addresses? Okay, yeah, here's a list. And also Google DNS and OpenDNS publish the source addresses they're going to use for traffic. So we consider those to be good enough, and we analyze the traffic we see from those source addresses. Also, because we need non-resolvers, so known non-resolvers, we check our traffic and find all the monitoring addresses from ICANN that are asking for this string, www.icann/monitoring.ccTLD or TLD, and some addresses sending just only the NS queries. We thought, okay, that's our training data. So we did an exploratory analysis of this. We have a blog post with all the details. but the conclusions were mainly there are some patterns. So you have the primary and secondary addresses for resolvers. So when an ISP sends you the configuration for your client on the DHCP negotiation, they will send you likely 2 addresses. So the clients will mainly use the first address. The second address won't be that much as used. We also see some validating resolvers. So according to Geoff research on DNSSEC validation, New Zealand has a 50% level of DNSSEC validation, so there are few large ISPs doing validation there. And there are a couple of resolvers sitting in front of mail servers, so they get a lot of MX queries. So there were some patterns, there were some commonalities, there were things that were not that common. By the way, I find really fascinating, so I'm going to talk about supervised learning here. But this is the third presentation that actually mentions machine learning during this workshop. So the guys from Syra were talking about that before, and yesterday Chris Wood as well. So there's interesting twists, something coming there. So can we use supervised classification in order to predict a source address? So we picked 14 features. The fraction of traffic coming from a given address against the total traffic. So that's a number between 0 and 1. The fraction of the responses that generating, how many of those are for existing, so they are referrals or empty responses or NX domains, and how many of those have the CD and the RD bit. So that makes 14 features we will use to go and train a model. And we use as training data 1 day of traffic, so that's the 653,000 unique source addresses. So we train the model, we use linear SVC for this, and we get, this is just to show off, so there's nothing useful here. So it's mainly saying the accuracy of the model is 100%. So all the data provided, all the training data, it fits perfectly. We also tried with k-neighbors and random forest, and all of them achieve 100% accuracy. So problem solved, I'll walk away, have a good coffee. No. So we apply, once you train the model, you have to go and test it and use test data for this. And checking the numbers, we identified most of the addresses as resolvers. That's wrong. That doesn't make any sense. So it's very unlikely we will have 645,000 different resolvers talking to us in a day. And using the same different dates for data to test the model is more or less follow the same pattern. So the post-mortem analysis of this model led us to think that we actually were overfitting. So this is a common term in machine learning. You overfitting your model. Basically, what the model is catching is not the resolver behavior, it's the non-resolver behavior. So our model was finding most of the non-resolvers, but not the resolvers. So we thought, okay, let's try a different approach and go away from the supervised learning and do unsupervised learning. So let the data to tell us what kind of a structure is inside. So instead of imposing the labels for the addresses, we go and use the same 14 features, the same date of data, ignore all the clients sending less than 10 queries in a day in order to reduce the noise. And we run clustering algorithm, k-means, with k equals 6. So this was inspired by the work that Matt Larson presented in the RIPE meeting in Dublin like 3 or 4 years ago. And I think that's where Dwayne was involved. at that point. So we extended that a little bit, and we use Python for this instead of Java. So we try to calculate. We have these labels. We have the source addresses. Let's go and find which bucket or which of the clusters the resolvers fit. So yk equals 6, you usually calculate the cost curve, so the internal inertia of the data, and you see the trend downwards around 6 or 8. So that's the value we picked. So for each profile, so we have 6 different groups or clusters of traffic. You see the 35.34% of the source addresses match this pattern. Then you have 27% matching the group number 5. Then 50% matching number 3, and so on. And finally, you have 1.5% roughly that's sending most of MX queries. So we have 6 clusters. And this is the same for the response distribution, and this is the same for the flag profile, so CD and RD. So we check the clustering accuracy. So how many of the non-resolvers fall in the same cluster? And the answer is, so the cluster number 1 covers 99.05% of the non-resolver addresses. So that's pretty good. And for the non-resolvers fall into mainly label number 1, which is the same as above, label number 2, and 1 in the cluster number 4. So there is a split good enough for the resolvers, but not good enough for the non-resolvers. So we thought, well, a resolver is likely to be very persistent in the sense of sending, because it's deploy infrastructure, it will send queries to us regularly. So it should go, well, one day I will send a few queries, the next day I will say another few queries, and then it will stay a long time. So we took out 10-day rolling window, and we count how many of the resolver addresses were seen on a specific number of days. So we were feeling, the resolver addresses will be sticky, they will stay there. So you can say there are different shades of blue. So the white one on the bottom is addresses that on that 10-day window send traffic every single day. And then just 9 days, and then just 8 days, and until the blue ones that send only 1 day. And this is the number of addresses. So you see there is a very stable number of addresses that send traffic most of the time. And then when you start reducing the number of days, you start seeing the patterns between weekdays and weekends. That's another observation. Actually, I work with it with SIDN at some point about traffic tracking, validating resolvers. And validating resolvers see less activity during the weekends, which was interesting. I don't know if you've seen that data on that kind of results on your data, Geoff. So are we matching the hypothesis of persistence for resolvers? So if we check the presence of different days, this is only the list of non-resolvers. Most of them send, so you see there is a little bit of pattern around weekdays, weekends, and weekdays, but you see most of them, like there is a baseline of 700 out of roughly 900 that send queries every single day. So yes, we have a pattern there of persistence plus traffic. So that's the work. We haven't finished this work because one of the failures we have at the beginning was the list of non-resolvers. We need to go and extend that.
but we also want to identify resolvers we don't know yet, that not in our training data, by exploring the resolver-like cluster. So that was like cluster number 1. We will be very happy to share this information with other operators. At some point, not for this work, for a different piece of work, we were collaborating with SIDN about exchanging how, for example, resolvers in New Zealand send traffic to their infrastructure and the other way around. So if you have addresses to feed on this, or if you want addresses from us to feed into this, we will be very happy to share. Well, the potential uses of this list of known resolvers is, for example, whitelisting or capacity planning. For us, it's for the domain popularity ranking, but there are some uses for this. This analysis can be repeated for other CCTLDs, and it's using mainly open source tools. In case, yeah, I totally missed, but we have a big data platform for this, which is previous to Entrada, and the code we use is very easily adaptable for Entrada. We are basically using Python and using an Impala database in the same way as Entrada does. And we will make the code available for analysis sometime soon. Well, we didn't have the time to go and do the code review in order to make it high quality, but this is all, we are aiming for reproducible research. So that's me. My contact email is there. Probably you know me, and if you want to talk to Jing directly, that's her email. So thank you very much, and we have plenty of time for questions and coffee.
Yes.
Very nice talk. Thank you, John O'Brien, University of Pennsylvania. Sorry if I missed this, but in your client persistence results, you addressed the resolver case. It didn't look like you addressed the non-resolver case, and I was wondering whether my intuition that non-resolvers like monitoring nodes would look identical to this is on track.
Yeah, well, that's definitely a good point. So this is the client persistence across all addresses. So we have like 200,000 there. And if we go to the resolvers, we have 700 there. So there is a very large number of addresses we don't know what they are that are sending traffic every single day. So they might be resolvers or non-resolvers. That's a very valid question. Thank you.
Thank you.
Hi, Roy Adams from ICANN. Could you go back to slide 14, please?
14.
So what I see here, I just discussed this with Ray. You're missing. Oh, sorry, not you missing. What you haven't taken into account is R code 5, which is refused. If you would do that, sorry.
Yeah, we actually we started with all the R code, and the number of refused, it was like 6 or 10, very, very low.
Okay, then there's something wrong in your data, because cluster 2, which is the one on the right, this is actually the result of a botnet named Cutwell.
All right.
And the reason for that is it sends with RDBit, it sends NS, A records, MX records, sorry, Q types, and that is all in cluster 2. You can see here as well, cluster 2, the one on the right, mostly MX, a little bit of A, and a little bit of NS. And so, in order to amplify it, if that is indeed Cutwell, it would be good to have R code 5 there as well in that cluster 2. But also, for instance, the distribution of the identifier. If the identifier is below 256, then it would again be Cutwell.
Okay, that's a useful feature we can use for the training. Yeah.
Okay, then one more point. And sorry to hold you all up for coffee. Folks from CZ a couple of years ago did a very, very interesting kind of resolver profiling using a hashing algorithm, if I remember correctly. There's also some interesting stuff to look at. You can classify, for instance, if it's a company-based resolver, they don't have much work in the weekend, or if it's a ISP-based resolver, they do much in evening hours, etc., when people are not at work.
Okay, yeah,
So
that
that's kind
totally
of-
went under the radar. So yeah, I'll take another look.
Okay, cheers, thank you.
Thank you.
Jeff Houston, APNIC. I've sort of been looking at the same problem from the other way around.
Yep.
By basically seeding an end user with a known set of DNS questions and seeing which resolvers ask immediately, and because the name has time in it, seeing which resolvers ask later.
Oh, yeah.
And so the observation is that in my authoritative name servers, up to 35% of all the queries are shit.
Yeah, the zombies.
They're zombies because they've aged from a long time ago and someone else is requerying. And the resolvers making those queries are in different sets. So my question to you is, have you looked at the query rate once you do this classification? In other words, at your servers, once you've classified something as a, well, this doesn't appear to be a resolver acting on the behalf of users, it's some kind of monitor, what is the query rate you're seeing from that set? Because as I said, what I'm seeing is around about a third of all the queries I'm getting are not real queries.
Yeah.
Have you done that analysis?
No, we haven't done that, and we're planning to include not only the query rate, but also the inter-arrival time, because so monitoring hosts are likely to have a with very low variance between the inter-arrival query time. So they will regularly go and send the same query again and again every 60 seconds plus minus 1, for example. So that will be another feature.
The other data I've noticed is that around about 6,000 different IP addresses correspond to around 92% of the users.
Yeah.
So the core should actually be really common between both of these data sets if you want to compare them at some point.
All right, great, thank you.
Robert Edmonds, Fastly.
Hi, Robert.
There was an earlier slide towards the beginning of your slide deck where you mentioned the behaviors of the known resolvers versus the known non-resolvers.
That one?
You were describing the behavior of the known resolvers and the known non-resolvers.
Ah.
And I think you mentioned addresses sending only NS queries. How did you come to the conclusion that sending only NS queries means it's a non-resolver and not, for instance, like a resolver that implements query name minimization with Q-type NS?
Well, I didn't expect to see a lot of implementation of. So that list is, I think, is roughly 200 addresses doing that specific pattern, and this data is from March this year. So I wouldn't expect to see a lot of QA minimization activity at that point.
Okay, thank you.
I could be wrong, so I'm not expecting to defend. No, I'm absolutely right on this.
Right. I mean,
I can observe
I think
that.
it would be possible for by March for there to have been released versions of, I think Unbound specifically had a release that supported QA minimization.
Yeah. Thank you.
All right.
Yeah,
Thank
I
you
think
very
I'm
much.
done. Thank you very much
Sebastian.
for the feedback.
So we are now at our coffee break. We will meet back here at 11 o'clock for the next set of presentations. And yeah, I think that's it. Thanks, everyone.
Right, we've got a couple of talks coming up from John Heidemann on the root system and Anycast. Interleaved between those two, we have Vincent Vigneron talking about ENT was here, the mystery that's perplexed some people on the DNS operations lists. So, John, without further ado.
Okay, hi. So, for folks who may have downloaded the PDF before an hour ago, if you have rendering problems, you might want to get the updated version. They were fixed very recently. So hi, I want to talk to you about Anycast and latency. And this is joint work with Ricardo Schmidt and Jan Coopers from University of Twente. So we all know why we do latency, right? Why we do Anycast. We have multiple sites around the world, and hopefully you get to a close site when you access things. This is the PDF? This is the PDF. Can the laptop? Oh, I gave them PowerPoint. And I talked to them about it 20 minutes ago. You got that one, Jerry? Just a minute.
Sorry, just one moment. I'll try and get the right slides on.
I talked to them about it yesterday.
Okay. Shouldn't keep you long.
Apologies. Sorry. Oh, I have to unplug the mouse. How will we mouse? Somebody's moved. Well, are you going to start it or am I? Whoever has the remote desktop. Thank you. Okay, so let me try this again. See, look, beautiful animations. So the idea of Anycast is that you are going to connect to some site, and your friend who's in a different place has his animation screwed up. Oh. Gets to talk not to the site that's far away from him, but the site that's closer to him or her. And so the point is, when we have a service that's distributed around the globe, you get lower latency. And that's one of the reasons for the use of Anycast. Not the only reason, but the reason that this is the focus of this talk. And BGP is the glue in the middle that lets us find the close site. And this is used by DNS. It's also used by a bunch of CDNs. So we've put a lot of money into Anycast. A lot of different people have put a lot of money into Anycast. This is the DNS root system off of rootservers.org. And there's a whole bunch of sites around the world. And there's a certain expense behind this, both in terms of hardware in the field and also, paying for all those bits and all those power cords and ports. So one might ask, from a latency point of view, does Anycast work? Are we getting what we pay for, or what are we getting? And that's what the point of this talk is to try to address. So it's important to think, what does work mean in this sense? If we're talking just about latency, and again, I want to rule out other kinds of things like denial of service defense. We'll talk about that later. Does Anycast give good absolute latency? And the other question that this talk is trying to deal with is, do we get optimal latency? In other words, if you have 10 sites around the world, are you getting the best possible latency that you could get from those 10 sites? And we're going to answer those questions with some measurements using RIPE atlas. So the ideal with Anycast is, as I said, you put people around the world, and we can think about it dividing the world up into catchments, right? The space of the internet that is covered by each site. Unfortunately, that's not exactly what happens in reality. So this is data from Ray Bellis, who was optimizing froute using ripe atlas. And the red dots on this graph on the left are the places that had latency greater than 200 milliseconds. And you can see there's a whole bunch of red in Europe, yet F has a bunch of sites in Europe. So what's going on here? Why are they taking 200 milliseconds? Well, when you spent time debugging that, it turns out routing is hard. And a bunch of sites in Europe were going to Atlanta because we all like peaches, I guess, or something. So Anycast does a lot of good a lot of time, but you got to be careful with it. And finding these kind of performance bugs is something that takes time and is important if you want to get optimal performance. Okay, so that's some evidence that we're not necessarily always getting optimal latency. Let's talk about what we measure in this paper. So our sources are on the left. We start from, at this time, about 7,000 ripe atlas probes, these little embedded devices around the world that happen to be measuring the root system, which is very nice of them. And then our targets are the 4 roots on the right, C, F, K, and L. And we pick those for a reason that I'll give on the later slide. But the neat thing is, from our point of view, they're operated by different people. They all have different architectures. And they have very different numbers of Anycast sites and different routing policies. So it lets us really look at some different configurations here. And our data is taken at different times, and we measured K twice. Okay, so let's talk about how we do the measurements so you understand what's going into this. So as I said, we think of the world as divided up into catchments. So the first step is, how do we know for a given vantage point which catchment it's in? And the ripe atlas system is already taking this data for us. They do chaos probes against hostname.bind. That different servers that respond to that return a special code. And from that code, if we parse it carefully and use a little bit of magic, we can figure out which site you're at. Okay, so in this case, for this fictitious route, you might get back sjc1.x.rootservers.org. That tells us it's in San Jose. SJC is the airport code. So that's what we'd like to see happen. And if you do this from a whole bunch of vantage points around the world, you'll get different answers telling you about different catchments and where each vantage point, which catchment it's in. Okay, so that's the basic thing. How do we find catchments? And lots of people have done this before, and this is what the froute people use to optimize their system. And people have looked at this, 10 years ago, the catchment assignment. So the new part of what we're doing is, in addition to measuring catchments, we also want to know the latency to all possible sites. And this is an insight. If we take that data, the catchment addresses, if those chaos strings that are returned happen to be the unicast IP addresses of those sites, of the catchment that you're getting, then that's very convenient, and we can use that information to find the sites. And that applies to the 4 routes that I mentioned. It does not apply to all of the routes. And it's a convention that they choose to follow. There's no standard here. Okay, so if we take that information and instead of just using chaos probes, do ping to each of the sites, to each of the unicast addresses for all of the sites from each vantage point, then we know not only which catchment you're in, but we also know the latency to all the possible catchments. To all the possible sites. And that lets us get, so we know that our person in Los Angeles, how far away they are from all of the other places, and the same thing from the other sites that we look at. So this is what lets us judge not just what catchment you're in, but what your optimal catchment could be if you were just optimizing on latency. Okay? So the key takeaway is we know where you are, and we know where you would like to be based on latency. So let's get to looking at the data. So the first question we ask is latency good? And the basic answer is yes, for the most part. If we look at median latency, so the 50th percentile, latency is pretty low. It's around 30 milliseconds for the routes that we studied. And that looks pretty good in terms of responding to occasional route queries. So it is important to note that latency in the tail gets quite a bit higher, and that's something we'll look at in more detail later. But the real question we had is not just is latency good, is it low, but is it optimal? Are you getting, whatever your Anycast system is, the best possible latency that you could? And there the answer is pretty happy as well. Across the 4 routes that we could study, the penalty, meaning of comparing what latency you're getting for the catchment that you're assigned by BGP versus the lowest possible RTT to all sites, is only on the order of 2 to 10 milliseconds, so not very high. And you can see if you compare the dotted and dashed lines in this picture. So you can ask, though, why would it be different? Why would you not get the best possible latency? And as I said earlier, it turns out routing is hard. And BGP is not necessarily there to optimize latency. It's there to do a bunch of other things. So one question is, how much is routing policy interacting with what's going on here? And so it happened to be, over the course of our study, KRoot changed its policy and moved most of its sites from local Anycast, where the Anycast site is serving only the AS, or maybe the AS and its clients, or customers, I should say, to most of them, all but one of them being global Anycast, so being willing to serve anywhere in the world. And what we saw is, if we look at K before and after this change, the blue and pink lines in this picture, there's almost no difference in actual latency. Oh, wait. Okay. No, I better not do that. There's almost no difference in actual latency, the solid lines, and there's only a slight difference in optimal latency. So our observation from this is that change did not make a big difference. And hopefully, therefore, policy issues don't usually cause you a great deal of penalty. What we did find makes a huge difference, though, is location. Where are your Anycast sites placed? And we do this with 2 simulations. To understand this question, we do 2 simulations. So in each simulation, we take the data that we have. In this case, we're starting from C-Routes deployment. And we take subsets of that using only certain sites. And on the assumption that people go to their optimal site, which is an assumption we've shown is pretty close to reality, we can then imagine fictitious Anycast configurations that are subsets of a given route. And so we play out 2 of those scenarios here. The graph on the left shows fictitious setups where we pick one Anycast site and then we add additional Anycast sites. And so there's no way I can get a cursor on this thing so I can point? I guess not. Okay, so if you no, well, I'll survive. So the graph on the left, the light blue line in the center of the graph is if you had only had an Anycast site at LAX. And then we add on the next line an Anycast site at Chicago. And then we add an Anycast site at Washington, D.C. And then New York. And what you can see is each time we move eastward, our line shifts to the left. Our latency, our mean latency gets lower. And this is for 2 reasons. One is we're spreading our Anycast sites out. But the other big reason is RIPE Atlas, mostly in Europe. The RIPE Atlas probes are not uniformly distributed around the world, so there is bias in our measurements here. And the CDFs, the lines that I'm showing, are heavily weighted to European, being close to Europe. So that shows, the graph on the left shows a pessimal choice of Anycast sites. We're adding sites moving just incrementally eastward. The graph on the right shows the optimal choice for this, for taking subsets of C-route. We start with the with the light blue line with one site is Charles de Gaulle, the Paris site. And then we add a site in LAX and JFK, splitting the difference. And as you can see, each addition makes it a little bit better, but pretty much you got most of the bang for the buck by just being in Europe, or being in Europe and the United States. And so our argument from this is that, boy, location really matters. Just getting physical geographic spread of your Anycast sites makes a big difference because you're fighting against the speed of light latency of communication. Okay, so that's location. So this, up till now, we focused on the median latency and what happens around the 50th percentile. But the other reason you might do Anycast is to deal with people who are far away, or people in the tail of the distribution, people who have long latencies. And in particular, one would be concerned about people in countries that are distant from where your sites are. And so to look at that, these two graphs break out by each country what the mean latency is, the median latency, and then the bars show quartiles, 25 and 75 percentiles. And so what you can see here is for cRoot, well, we'll take away two things. So the first thing is, if we look at the tail, meaning the countries which have the highest latency, you can see when LRoot adds a lot more sites, they push that tail down. They're getting out physically around the world, and they're able to do a lot better in a lot of different countries, and in particular in the countries that have the largest latency. And so if you arbitrarily define high latency as 100 milliseconds, you can count, we go from 38 to 21 countries. The other thing, though, that you can see, though, is even with 144 sites, which was how many L had at the time of this measurement, there's still a lot of variation inside of a lot of these high latency countries, the countries that have high median latency. And when we looked into that, and in particular when we focused on the Philippines, where there are only 20 vantage points, we see that 7 of those stay inside the Philippines and get low latency. That would be the low end of the curve, the low end of the bar. But a whole bunch go to the US and Australia, right? And so the takeaway here, you can either have two possible takeaways. Either routing is hard and there are some kind of routing bugs, or another possibility is that infrastructure is hard and the Philippines may have less connectivity inside the country, making it difficult to get everybody in the country to the Anycast site that's there. So both of these are things to look at. It's not clear that these are necessarily under the control of the root operator, but they are challenges if you're trying to bring down especially the tail latency in countries that have less mature internet infrastructures. So the takeaway is, lots of sites can help you push down your tail, but you have to be careful in the tail and continue to deal with routing challenges. So what matters most in this? Well, dealing with routing, optimizing the actual Anycast. And so if you look at overall actual latency, F does slightly better in a range of the tail, even though most of the letters that we measure get similar performance. F seem to do slightly better. And there's a reason for that, which is they were teaching to the test. So they optimized against RIPE Atlas a few months before we took our measurement. So one would expect them to do well because they tuned against it explicitly. But it does show, so I wouldn't focus too much on that difference, but I think the thing to focus on is actually dealing with routing bugs and detecting anomalies is the key important thing. And we saw that same thing when we looked at countries that actually host Anycast sites. And this is challenging because, of course, it's not that this is not working. It's just that it's not optimal latency. And it's always difficult to go from, people are very good at reporting not working, but reporting slow is much more difficult. So in the end, the title of the question is how many instances? And if we just think about latency, so not thinking about denial of service or policy reasons or other constraints, I think if you think about speed of light, you could get by with a relatively small number of Anycast sites around the world if your target is to get 30 millisecond latency. And so the number we picked is about 12. If you think about 2 per continent or so, that should get you to that target. Again, though, location matters and debugging your routing really makes a difference. And of course, there are other reasons to Anycast. But that's relatively comforting if you think about getting good median latency. So just to wrap up, there's a whole paper with all kinds of details you can dig into if you want. The data is available if you want to reanalyze our data or see what you think. And big thanks to RIPE Atlas for many, many measurement credits. So questions, I think. I have no idea how much time we have left.
We've got up to 10 minutes.
Hi, Matt Larson, Can I just confirm how you calculated what optimal is? From a given Atlas probe, did you ping every unicast address of a given every unicast instance, or sorry, did you ping the unicast of every Anycast instance, and then whatever is the lowest for that?
Yes.
Okay.
So exactly. And so some caveats there. We're assuming that Anycast routing and unicast routing converge on the same thing. We're assuming that the unicast IPs we got are correct and complete and all that, so there's, but I think for the letters we studied, those are reasonable assumptions.
Okay, I haven't worked much with RIPE Atlas. Do they know the physical location of every probe?
That is data they provide, and we generally believe it to be correct.
Because it would be interesting to do, the actual great circle distance between a probe.
That's a great idea.
And
I've
calculate.
seen some people have done analysis of that before.
We did some similar stuff at Dyn internally, but nothing published for optimizing Dyn's Anycast network.
That's a great idea. So obviously, I had a definition of lowest possible latency, which was what we could measure from unicast pings. Ultimately, the lowest possible latency is, speed of light, or speed of light in fiber, depending on how you want to call it. So yeah, one could look at other kinds of optimals, and physical distance is a great number. Bill?
Bill Manning, sort of semi-retired and interested in this as an interesting circus. You talk about 2 per continent, and you speak about continental things, which, if you look at underlying infrastructure, the underlying infrastructure has a fair amount of dynamic nature to it as people add capacity, new exchange points come online, things move around. Over the course of this study, was there any consideration of topological changes underneath?
Yeah, so that's a great question, and it occurs to me there's another caveat I should add to my two per continent, which is it's also on the assumption that you have good intercontinent connectivity, and that's something we know is not always the case, as the Philippines example showed, or doesn't seem to be the case. Did we see changes? We did not. So the only before and after picture we looked at was K-root, and there we only looked at policy issues. So I don't know the answer of did unicast timings get lower, indicating greater interconnectivity? That's a great question, though. So thanks.
Joe Abley. So I had 2 comments. One of them was, of the root letters that you compared here, there's one interesting difference for one of them, which is that, if I'm correct, and root ops in the room can tell me if I'm wrong, but C-root used to be operated just in Cogent's network. It's just in AS174. They're not dealing with anybody else's networks. So when it comes to optimizing delivery towards a particular exit towards a node, they have complete control of the surrounding network, which in a way that the others don't. So that might reflect some of the differences in some of those curves being closer to the left for C-root than others, because they have more control and less variability. So that may be worth noting. The other thing is that, I work for Dyn, and we know perfectly well that RTT to our Anycast instances is very important to our customers and causes a lot of exciting phone calls. For the root server system, I appreciate this is just an easy-to-measure example to prove a general point, but for the root server system, I think a better metric might be the path diversity to all the available root servers, given that availability tends to be more about what you care about for a root server system than RTT. You don't send that many queries to a root server, and in fact, most of the ones you send are junk. So when you actually get an answer and you cache it for a reasonable amount of time, having the path diversity to be able to reach any root server of the 13 is arguably more important than being able to reach one. And in some cases, if that means that you have 5 paths, but they're all high latency versus one which is really low latency, the low one looks great unless you lose it because a cable's cut or something else is going on. So for the root server system in particular, that may be another metric to look at, not just latency, but how many options do I have to reach one of them?
I think that's a great idea. This talk was focused specifically on latency. You might hear a little bit about denial of service shortly, and looking at path diversity in that context is, I think, a really good idea. Thanks.
This is Andre Suri from CZNIC. I have 2 comments. It always saddens me so much when I see chaos.txt as a getting the name of the server, because we have NSID since 2007, and I just did a quick measurement, and only 6 of the 30 name servers measured from this network support NSID, so it would be great if we can get NSID support for more root servers. The other comment is about the RIPE Atlas measurements. Because the RIPE Atlas is better to measure the end users, but the root server users are not end users, but the recursive services. So optimizing for the RIPE Atlas probes means that you optimize for the people's homes, and that's not what you want to do. You want to optimize for the recursive services for those networks, and that might be very different in terms of latency.
So that's a very fair comment. You're right, we care about recursives, not home users. Our goal in using RIPE was to get geographic diversity, and it's not perfect in that regard, but it's better than any alternative that we have available to us. That said, so our data may be biased, and we know it's biased towards pro-Europe. It may be biased in other ways. That said, I think optimizing for geographic diversity is a pretty good approximation for optimizing for recursive locations, until I know better. So, anyway.
Hi, John Amazapinik. But once upon a time, I got to install the first F-root Anycast back when we started doing that. I have to say, similar to what Joe just said, latency at the level of the root servers is basically not important. That was never a reason why we did any of it. Though, of course, we put it in press releases and so on, because it was really easy for people to understand that. But the two fundamental reasons were resilience of the system. So is the root going to continue to be available if there is a network event, if the network gets partitioned, if you are on the wrong side of the fiber cut? For instance, when there was this earthquake in Taiwan that cut off Hong Kong from the US, that was the important thing. And the second, which is harder to measure, was giving some people operating networks in remote places of the earth a sense of inclusiveness. So a human value, which is very hard to quantify. That was very important. Lowering the tree, it's important, how you deliver how fast you deliver the service, but at this level it wasn't. So a really useful study would be to see how do you reach the different Anycast nodes and then try to simulate an incident in an AS path, an AS in several AS paths, to see who would be left out, and determine that, because that would be the real optimal placement, the one that ensures that service is not lost in spite of network events that actually happen. Red Sea cables get cut, earthquakes, whatever.
So I'd encourage you to stick around for an hour. We can talk a little bit about a network event that actually happened and how it affected specific users.
Okay,
so
great.
I agree with you.
Yeah.
And I try to be very clear in this talk. This is focused on just the latency question. I absolutely agree with you. Inclusiveness and involvement is one metric, as is resilience in the face of attack. However, this study was designed to try to address the latency problem so we could stop arguing about it. So I think that we agree much more than we disagree. Anyway. Okay. Well, thank you.
Okay, thank you, John.
So while we're changing speakers, can you copy the other talk to the local disk? Please.
Okay.
I don't know who has remote control of this computer. I'm sorry. Can you copy the November 30th PowerPoint? That file, please. Thank you. I'm sorry, please.
You got that, Dave? In a moment, Dave will put it online. Okay, so now we have Vincent talking about empty non-terminals and some edge cases with DNS Sec.
Okay. Good morning, everybody. My name is Vincent Villeron, and I'm part of AFNIC. So my presentation today is about an issue we had with DNS Sec validation last spring, and we faces many issues, and I'm going to explain how we have to deal with and what happened exactly. Some information about AFNIC in brief. AFNIC is a non-profit association founded in 1998, and we mainly operate 6 ccTLDs, .fr and other TLDs related with French territories. The largest zone is for .fr. We are also backend registry for about 14 GTLDs, like .paris, .bzh, and other strange ones you probably don't know, like Florgans, etc. And we host about 3 million domain names. And for DNSSEC, it was introduced in September 2010 when the route was signed. And today we have about 10% of domain names which are signed. Some information about DNSSEC, the way we operate it at AFNIC. We use HSMs. The kind of HSMs we use is AAP Keeper, and all our keys are stored in the AAP Keepers. We use 2 kinds of tools. One is for key management. It's OpenDNSSEC. I guess you all know what is OpenDNSSEC. We also use a bind to sign zones. And we also had to create homemade scripts to control, to synchronize, and to update and distribute keys to make the link between OpenDNSSEC and bind. Our zones are dynamically updated every 10 minutes. And we chose to use NSEC3, and salt is changed several times per month. And for the records, keys and salt are not shared amongst ccTLDs, and each TLD has its own keys and salt. We roll over KSK every 2 years, and we use standby keys. It's not very common, but it works. So we have 2 DS present in root, but only 1 KSK is published. And we roll over ZSK every 2 months. So what happened in spring? In fact, we received a very detailed alert from Florian Maury from ANSI. I explained just after what is ANSI exactly. And he gave us a lot of details. He was not able to reach some gouv.fr domains. For the record, gouv.fr domains are domains used by French government. For example, if you want to pay taxes, you have to use them. So he was not able to pay his tax, so he wanted we fix it. So he told us that the DNSSEC validation was broken, and he found out that at least 1 instance of our Anycast server d.nic.fr didn't reply properly in case of denial of existence answer. And he received a lot of serve failed when he queried gouv.fr DS. So what is ANSI exactly? ANSI in French is Agence Nationale de la Sécurité des Systèmes d'Information, which in English more or less means the national authority in the area of cyber defense, network and information security. And ANSI main missions are prevention, defense and information. And they are transversal actions that covering French governmental organizations, critical operators, and the general public. And they also provide guides on network security topics like DNS, BGP, DDoS prevention, etc. So when you receive that kind of alert, I guess this is an alert that have to be considered very seriously. as many others, when we have a DNSSEC issue and when we want to show what happens to our managers, we use DNSVs. And in fact, we see that something is wrong. There are two errors that are detected by DNSVs for group.fr. So first, we had to fix the validation issue. So we had to find out what was wrong and how it was possible to fix it. First, we find out that all instances of our Anycasted service did.nic.fr had the same issue. It was not only the ones that was detected by Florian Morin, but all of them. But only them. We have other servers that host AFNIC CCTLD, but only .nic.fr had the issue. Then we realized that all of them run NSD. This is the only thing that is different from other servers we use. And authoritative servers that run bind and used by AFNIC do not have the issue. So before to understand what was really wrong, we decided to stop all NSD servers and switch to bind as long as we don't know what is wrong with NSD. And after the switch, everything was fine. There was no validation issue anymore. But in fact, what we did not know is that there is other things that was wrong, and we were about to discover more issues than expected. How we host our TLDs? In fact, we use different Anycast. One is operated by IC, another by PCH, SIDN, and network node. They all work very fine. We have absolutely no issues with them. And the one we had issues is the one we operate, and with a lot of surf failed when it uses NSD. This server is, except for a server which is located in African regions, all instances of our Anycasted server are located in Europe, but they have a very good connection, so they receive lots of queries. So we had many customers impacted by this issue. But now it's time to understand what is wrong. What we are sure is, I guess we are sure because sometimes you can have bugs in tools, but we are sure that .fr zone is error-free. There are no errors. We use many checks to verify the zone during the process to create the zone file, to update the zone file. We had many tests. We test DNSSEC validation, we test the integrity of files, and we are pretty sure the zone file is error-free. But why group.fr has an issue? Group.fr is not like other domain name we have, because it's an empty non-terminal domain. And in .fr and RE zones, we check and we notice that we have 8 empty non-terminal domains, but only 4 of them have the validation issue. .fr and RE zones are signed. We use NSEC3 and with the opt-out option. And as I told you before, keys are in HSMs. Zones are signed with bind and are dynamically updated. And because it's an empty non-terminal domain, group.fr is also signed because the .fr is signed. What we find out is that broken empty non-terminal have no signed subzones. And when you query these 4 broken empty non-terminal, you receive a CFR, of course, and NSEC3 records are missing. DNSSEC is not very easy. NSEC3 is not easy also. And if you mix NSEC3 plus empty non-terminal, it's not easy at all. It's explained in two RFC, the RFC 5155 and 7129. And there are two ways to deal with empty non-terminal, the exact match method and the covering method. N63 opt-out and empty non-terminal is not common, and RFC 5155 has an errata just for this case because it was not clear enough in the original RFC. But which method is supposed to be correct? What can we see in the RFCs? In RFC 5155, you can read that each empty non-terminal must have a corresponding N63 resource record unless the empty non-terminal is only derived from an insecure delegation covered by an opt-out N63 resource record. This is the case for group.fr. And in the other RFC, you can read that when using opt-out, names that are an insecure delegation and empty non-terminals that are only derived from insecure delegations don't require an N63 record. According to my understanding, that covering scenario seems to be a reasonable one, and it should work. But if you continue to read the RFC, in the same RFC, you can read that a recently discovered corner case, the one described in the errata, shows that not only those delegations remain insecure, but also the empty non-terminal space that is derived from those delegations, etc., etc. A way to resolve these contradictions in the specification is to always provide empty non-terminal with an N63 record, even if it is only derived from an insecure delegation. So it seems that exact match scenario is also to be considered. So for N63 and opt-out cases, there are two ways to deal with. So what is wrong with NSD in that case? This is what happens when it works. In the N63 covering case, when you query, for instance, in this example, it's a press.fr, which is also an empty non-terminal domain, you receive two records corresponding to the Apex Start of Authority record signed. The Start of Authority and the signature. You also have two records corresponding to the signed N63 record corresponding to Apex. You can easily check that with command N63H, and you can see this is the correct hash. And you also have a covering N63 record signs. So in this case, it works. If you have an exact match case, you have less records. You have, in the answer, you have the Apex Start of Authority record signs with two records and the exact match signed N63 record. And you can check in this case, this is the empty non-terminal queried is aso.re. If you use N63 hash command and aso.re, you can see that this is the exact match hash. What happens when you query NSD when it doesn't work? In fact, when you query just for instance, com.re, you just have the Apex Start of Authority record signed. That's all. The N63 closest enclosure is missing. And this one that is very important. When it's missing, the validation can work, and you receive a self fail. There is a different kind of answer that doesn't work, and that you can receive with NSD also. In this case, you still have the Apex SOL record signed. You have a signed NSX3 record corresponding to Apex, but this one is useless in this case because there is still the NSX3 closest enclosure, which is missing. Depending the tool you use, you will have a different behavior. If you use bind as a signer with the DNSSEC sign zone tool, it uses the covering method. If you use OpenDNSSEC as a signer with the LDNS library, it uses exact match method. In our case, if we use OpenDNSSEC instead of bind tools, the issue doesn't exist, but bind is not wrong, and we cannot change our DNSSEC publication system easily. OpenDNSSEC, for instance, does not support dynamic updates yet. It should in the near future, but it doesn't support it yet. And for us, there is no reason to switch to OpenDNSSEC now. So if you are a registry and if you have that kind of configuration, you should consider to check if you have empty non-terminals that have the validation issue. So if you use NSX3 with opt-out, if you use bind as a signer, is your empty non-terminal has no signed subzone, and if you use NSD as authoritative server, you should have probably validation issues. We send emails to NSD and NSVs, and it was fixed very, very fast. For NSD, a few days after the issue report, a fix was available in the repository, and a new version was released very, very fast. And this release fixed the bug. So if you have an NSD version previous to 4.1.10 and 3.2.22, you have the bug, but the new version are correct for this specific case. And for the NSVs, there was also an issue on the interpretation of RFC on the errata on RFC 5155, and it has been fixed very fast. So from our point of view, now everything should be okay. But in fact, it's not just a tool issue. There is still an issue to deal with, because we discovered that Google Public DNS didn't deal with empty non-terminal properly. Even when we switch from NSD to bind, it doesn't work if we try to resolve using Google Public DNS. We still have a serve fail if gouv.fr is queried. This is still a validation issue. But it works when we query DNS over HTTP service from Google. So we find out that Google Public DNS doesn't work properly when an empty non-terminal is queried. We can fix Google Public DNS, of course, but we found a way. It's not the best way, perhaps, but it was the only way for that. We decided to transform empty non-terminal domain into non-empty non-terminal domains. So we had a TXT record in all of them, the 8 we have, because in this case, all of them had the validation issue, not only the 4 that had the validation issue when we used NSD. In this case, all of them had the validation issue. So we are obliged to modify our scripts to deal with that kind of exception. And the text says, the TXT says, empty non-terminal was here. And after that, that addition of the new resource record, it works. We had no more serve fails. When you add a TXT record and other kind of record, NSX3 covering record is replaced by a NSX3 exact match record that works with Google Public DNS. We don't know how many TLDs face that kind of issue, but we know that other TLDs have that kind of record, We don't know exactly if it addresses the same issue. For example, there is in co.jp a TXT record for a long time. Perhaps it addresses the same issue. We don't know. If there is someone from .gp, yeah, perhaps we could have an answer. We found several similar empty non-terminal in hosted zones. So we send an email to registries, and they have fixed their zone since. And the question is, do we have to fix all empty non-terminals until Google Public DNS has not fixed them? It's a service. From a statistic point of view, there are, perhaps it's higher today. I wrote this slide days ago, but there are about 1,500 TLDs in root zone, and many of them, most of them use NSX3, and most of the ones that use NSX3 use opt-out option. So we have 841 TLDs that may host a broken Google Public DNS empty non-terminal domains. So so after we had this issue, what we have learned is that we need to have different DNS software distribution ready to run on our authoritative servers. It was already initiated, but we decided to increase the priority of this project, and we call this project genetic diversity. So now we have decided that from now there will be a bind NSD and not DNS servers on all our authoritative servers. And we are still working on a configuration script that will allow us to create all configuration files from a Unix source. And we work on processes to switch from one DNS software to another very easily. We still need to keep the capability to manually handle data in zone files, even if they are generated. If we want to fix that kind of case, and we need also to add a specific regression test on corner cases when upgrading DNS server software. And a question arises among my colleagues is why create an empty non-terminal like group.fr? In fact, there are many reasons for that. For instance, a zone cut search during reservoir chain of trust creation, a QNAME minimization. We know in that case it has nothing to do with QNAME minimization, but it could have been. A name misspelling in an email or web, etc. And whatever, it's our client's right to create group.fr, especially as queries on domains in group.fr at correct answers. So we had to fix our servers because we must be able to correctly answer all queries. But we don't really know why this old but unknown issue had suddenly such an impact, because it was something which was not new, but suddenly it had a very, very important impact. So what to do next? So we still wait for a fix from Google. We reported them the issues. There is an issue number, but it's not yet their priority. They promised us that they will deal with that when they will have time, but we have no date for a resolution, for a solution. In the meantime, if you want to prevent any kind of DNS check validation issue to your customers, so you should check if you are using NSX3 with opt-out, check your zone to find if there are empty non-terminals, and you could add fake records to transform empty non-terminal into non-empty non-terminal, or switch to a signer that generates NSX3 corresponding records. And that's all. If you want to do some tests, there is a specific domain names we use for that, but that's all. Thank you.
Okay, thank you. We have just about 6 minutes for questions.
Hi, this is Paul Hoffman. I think you made a lot of good points, but I think you made one bad assumption in there, which is that it's only Google DNS that's going to have this problem. I mean, you saw it because,
Yes.
of course, they're the biggest one. I would be shocked if this problem didn't appear in other resolvers, especially ones that might be hand-rolled. Remember, people think, oh, it's the DNS. I can hand-roll my own software and such like that. And I'm not defending Google DNS. Quite frankly, when they saw this, they should have had this fixed within a day or two, just like, you know, the folks at NSD did. But I hesitate to say this, but I think because we don't know, you know, and quite frankly, a bug like this could be introduced later in resolver software that works. That someone rereads the RFCs and says, oh, we're doing this wrong, but no one noticed that and you know, fixes it. I think really the answer is don't have empty non-terminals, you know, put ENT as here. Roy will disagree with me.
Hi, Roy Adams, ICANN. With a few others, I co-wrote RC 5155. So I apologize for missing the corner case at the time. Could you go to slide 12 for me, please? So apparently this looks like a contradiction. Or slide 13, doesn't matter, slide 12 is fine. Apparently this looks like a contradiction. However, RC 5155 is a proposed standard, and it came out, I think, in March 2008. That's over 8.5 years ago. The errata, I happened to write the errata as well for this specific issue, came out, I think, in December 2012. I'm frankly, when I first saw the ENT was here records, within a day I knew what was going on, and I tested all the available resolver code that was available to me, and everything worked. I never thought about testing Google, but the resolver code worked, not realizing that the problem might actually be in the server. And indeed, the case is it's in the server. The problem with RC 7129 is it's an informational document. It's not a standard per se, and it comes out with a hack. For those who do not understand ENT or opt out, I have an analogy here. If, for instance, CNAME didn't work in your server, this proposal would say, you know what? This is a way to make CNAMEs work. Instead of an alias pointing to a canonical in a hostname record, you can basically have two hostname records pointing to the same address, and now CNAMEs work. What actually happened is CNAMEs are then gone. ENTs are just part of the protocol. RC 7129 proposes to just get rid of empty non-terminals by creating a record or creating a matching NSEC3 record. It's not necessarily wrong, but it's not fixing ENT, if that makes any sense. I'm saying this in general. This is not specific critique about your presentation. I think it's very cool that you guys actually found an issue almost 8.5 years after a standard is published, 4 years after a standard errata came out. And I think the authors of, one of the authors of 7129 works for the same company that builds NSD, so I'm quite surprised that still, in the last couple of months, there are still bugs in protocol bugs in well-known servers. So thank you for pointing that out. Cheers.
Willem Torop, NLNet Labs. You said that OpenDNSSEC does not support dynamic updates, but it actually does support IXFR in and out since September 2015. So I just want to comment that.
Okay, thank you. If there are no further questions, then thank you very much for that. I'll have John Heidman come back to talk about the non-latency issues with the root system.
Thanks. Oh, look at this. Great. You'll hit the go button. Thank you. Okay, so thanks for having me back. Yes, at least we'll talk about the DDoS issues with Anycast. So again, this is joint work with colleagues at 20 and also colleagues at SIDN Labs. Okay, so this is what happened at the root servers according to DNS Mon last November. And we don't like to see those red things. And so, you know, that's a lot of loss going on. And we were trying to understand what happened here. And in particular, trying to characterize what does this red really mean? Is red bad for everyone? What is red, or does red have a more subtle meaning here? And more generally than that, in this specific event, in these specific Anycast servers, what can we say about Anycast in general? Because Anycast is used for a lot of things. So that's the goal of this talk, to understand this kind of an event. And we know denial of service is a problem, and in fact, this slide is probably out of date, is it? So, you know, they're big and getting bigger. Yes, this is out of date. 1 terabyte is not possible. 1 terabyte has, well, almost happened. 960, I think, was the most recent high water mark. It's easy. You can buy Anycast. You can buy denial of service tags for a few dollars if you go to the right places, and they're happening all the more frequent. So what do we do with Anycast? Well, one thing we do with Anycast is put up, what do we do with denial of service? One thing we do is put up Anycast, because you have a lot of servers around in a lot of different places that can kind of absorb these attacks and protect from them. Right, so you saw this before. The question in this talk is what happens to an Anycast architecture when it's placed under stress of a lot of traffic all of a sudden? Okay, so in particular, how well does Anycast defend against denial of service? And the specific thing we do in this study is to use public data sources from RIPE Atlas and also BGPmon to study this event carefully and try to look at some of the more subtle things that are going on. And look at, and then the other thing is to look at design choices, not just what did go on, but what perhaps should go on, or what might go on, or how might you make those choices. And to study both this event and to generalize. And it's important to explicitly state some non-goals, so we're not, we're sticking to public information. We're not here to bash people who did better or worse. And we're trying to get a handle on the bigger picture. Okay, so the specific contributions are to look at this specific event and see what it tells us about Anycast under stress. And we want to be clear, we know people have looked at these issues before, but to the best of our knowledge, people look at this in private. And partly that's because you don't want to give the attackers any advantage. You don't want to tip your hand. So the other focus of this work is to be public about it, which is why I'm here. And apologies to those of you who know all about defending against DDoS in your own infrastructure. Okay, so before we look at this, I want to get some terminology on the table. You guys should know all of this already, right? We have a root, but in this talk, I'm going to talk explicitly about letters, which are, from my point of view, a bunch of different Anycast services, because each one is operated independently and has a different architecture, and most are run by different organizations. Inside of each Anycast service, there are a bunch of Anycast sites, which are at different physical locations, and some of those sites actually reveal individual servers inside of each site. And so we're going to walk back and look at what's happening at the sites for each specific letter that we can study their Anycast. Okay. So you've seen this slide before. You know that Anycast, we want to have people close, right? And we're dividing up the world into catchments. So let's think this time about Anycast under stress. So you're using your site at San Jose at this fictitious X route, and a bunch of attackers come and overwhelm that site with a bunch of traffic. And let's assume that's enough traffic that you're blocked out. Well, what should we do? Well, what happens to you, the user in Los Angeles, is your queries get dropped because the router's queues overflow and you're set. However, at another site, a site that perhaps has more capacity, perhaps that site can just absorb this attack. And so your friend in England might be just all peachy, right? And then somebody else in Australia might be just happy because they don't have any attackers in their catchment. So this is the kind of dynamic that plays out. So let's think about what we should do if we're operating X route here. Well, one thing is just do nothing, right? Only one person is hurt, or one person we know about. So that's one option. Another thing is we could try to shift our routes around and try to see what happens. And if we shift the routes in the right way, we could shift some of the attackers to hit a different target, a different Anycast site that has more capacity. And if that site can absorb the attack, we might be able to serve everyone, and that would be something we would strive to do. But there's a risk, which is if we shift routing incorrectly, we could shift those attackers somewhere else and spread the damage without protecting anybody. So how do we know what to do? Well, the bottom line is it's really hard to know what to do because, as I said earlier, routing is hard. And routing is not always under the operator's direct control because it's a function of all the ISPs between you and your users, and you don't maybe even know where your users are. And oh, by the way, you don't know where those attackers are. And you don't know what they're doing necessarily and how they're attacking. So it's really hard to make informed choices here. And I think it's important to recognize that. Yet it's also important to think, even if we don't know today how to make informed choices, what should we gather? What information do we need to make better choices in the future? And oh, by the way, maybe some of you know how to make better choices now, but talking about what we're seeing here. Okay, so let's turn to the data that we have, which is this November 30th event. We're going to see some kind of actions that take place. We're going to see how it affects clients as best we can, and how those results vary across different letters. And so the data that we're drawing on is RIPE Atlas, the same thing I talked about before. Very nice that they operate this service and do all this data collection that we can just download. We actually use more data in this study than appears in the DNSMON analysis. So DNSMON, I believe, uses only RIPE anchors, and we gathered all the data from all the RIPE probes, so we get a broader view. In this case, about 9,000 vantage points. At this time, they were probing every 4 minutes, so that's the data that we have, except for A-route, which for some reason at this particular day was not being monitored so frequently. So we can't study that as well. We're using chaos queries again, as you heard about before. Again, we map the chaos queries to sites. The other two data sources we use are RSAC0 reports for letters that we're providing them at this time, which was, I think, only 4 of them. And we use BGPmon to look at routing information from a bunch of different BGP vantage points around the world. And the picture at the right shows the RIPE Atlas probes at the time of the November 30th event from the right side. Okay, so what happened? So this is mostly drawn from public information at rootservice.org. Also, there have been a couple of other presentations, some at Oarc in the past. So there were 2 events lasting a couple of hours, or an hour, a couple of hours each. They affected a bunch of letters, not all. There were a lot of queries, and different routes responded or reacted or were able to absorb that traffic in different ways. Some letters had high loss. We'll see about that in a bit. And however, an important takeaway is overall, DNS seemed to work quite well. There was enough capacity for clients to manage this attack. But of course, we want to do better. So that's the point of why we're studying this. So the baseline from our data, so this, you can think about this as a fancier version of RIPE Atlas's red dots. We look at the percentage of RIPE Atlas probes queries that go through for the letters that suffered, in this case. We show the 4 that didn't show any change in the bottom right corner. And what you can see here is there's different levels of query loss from RIPE Atlas probes to each different letter. And oh, by the way, RIPE Atlas is probing only specific letters, so it's not able to fail over to other letters. That lets us study this in this case. And so this shows you the same thing as the red dots, right? Lots of loss. But I think we still need to look a little more carefully at what's going on in terms of lots of loss, because this is a global number from all the RIPE Atlas probes, and it doesn't necessarily say everything that's going on. So that's what we'll turn to next. So in this plot, we take that aggregate number and deaggregate it. So each line or each row in this data is one Atlas probe, and each column is the time series of which site it's visiting. And the colors represent different sites. The data here is for, and this is a subset of the probes that we're looking at K-route. And you can see the 2 colors. The top salmon color was reaching Frankfurt, and the bottom goldish color was reaching London. the London site. And then you'll see there's some blue in there, which is Amsterdam. And then white is other things, and black is what we don't want to see. Black are probes that try to reach their current catchment or their current site and don't get a reply. And what you can see here, first overall, while the prior graph showed that K did quite well over the attack, it had only 30% loss, this site shows that these 300 VPs, I'm sorry, 300, not 140, had a lot of loss, right? There's a lot of black in the two events, those two columns. And so the takeaway is that loss across the users is uneven. It's looking at this single global percentage is not representative of what happens if you happen to be in London at this time. And that's important for users to understand and to think about. So, so given this observation from a sample of sites, the next question is, well, what happens if we look across all of K's sites? And so I have a different rendering of that. So what we have on the left are spark lines for a number of different K sites. So each spark line is normalized to the median number of probes that reach that site over the 2 days that we studied. So you could think about Anycast as assigning people to sites through BGP. And the median number, if Anycast is stable, should indicate the sort of natural catchment, the natural people who are assigned to that site. And we see it's pretty stable for most of the time. There are two features that appear in these spark lines, though. One is these dips, where the number of sites reaching a site, the number of vantage points reaching a site drop. And that happens in both cases due to these events, because traffic is overwhelmed, the routers drop in packets. And then the other feature you can see sometimes is the lines go up, right? That's people moving to your site for some reason because routing has changed. So those are the two features to look for in these spark lines. And our question is, we see in these two events, and you can see on the picture on the left, there's sort of two sets of dips corresponding to the two events. I'm sorry, I didn't say this clearly before. There were two different events about 24 hours apart. Very convenient for experimental purposes. Anyway, if you look at these two events, you can see there are dips in a bunch of these events. And we want to understand what happens to those dips. So just because your Anycast site has fewer people coming to it doesn't mean they're all sad, doesn't mean they're all not getting responses, because it could mean they just shifted somewhere else. So we want to differentiate between people not getting service and people getting service at a different site. Okay, so that's the goal with these kind of plots. And what you can see are, if you look across all the sites, and in the paper there's the list of all 44, I think, sites at this time, you can see there were a lot of dips and there wasn't enough ups to provide service for everybody. And we kind of knew that from the overall statistics as well. Okay, so having looked at all sites, let's go back and look at individual VPs and see what's going on. And I want to look at these specific set of VPs down here because it's kind of interesting. So let's zoom in on that. So if we zoom in on just a few of these, 40 vantage points for the first event, you can see a couple of different kinds of behaviors. So some of those vantage points, this band at the top, are really happy at London Heathrow and are staying there, even though during the event, they only got a little bit of service. Others switched routes, and the route changed, and they shifted to the Amsterdam side of K. So you can see that by the second band, where a bunch of them go blue. And you can see when they switched, they did somewhat better, right? There's a lot more blue dots in that black band than in the top band. But they're still not completely happy. There's still a lot of loss because there's a lot of traffic. Some others flipped to other sites, and you can see in that white band in the third down from the top. And then others switched to Amsterdam and stayed there for a long, long period of time. I'm sorry, the second band actually switched back shortly after the event ended. So you can see there's a bunch of stuff going on here, a bunch of dynamics. And in fact, we can see those in other kinds of metrics too. This looks at BGP data to try to see, is BGP changing? Are the routes actually changing? And you can see both on the left is a count of the number of flips, a count of the number of vantage points that change from one site to another. And on the right is the number of BGP events. And it's a little hard to see, but basically for all letters, there's a lot more BGP events around these two events. So routing is definitely changing. And then the final thing I want to do is go back and look across all the sites of a given letter and use a different kind of visualization here. So in this case, we roll up the minimum and maximum number of vantage points that hit each site over the course of the 2 days and compare that to the median again. And so the median is this line down the middle of each plot, and then the minimum and maximum are the high and low bars on each point. And we ignore the stuff in red on the right because that has too few vantage points to be statistically significant. But when we look at the things on the left, the sites that have enough ripe atlas probes looking at them that we can make some judgments, you can see some sites gathered a lot of traffic over the course of the 2 days, right? They were picking up traffic as routing changed. And a bunch of sites lost a bunch of VPs, either because they were overwhelmed or because traffic was shifted away from them. And you can see that in both letters. I think we have E and K here with, I have no idea who's, oh, E is on the top, I'm sorry. Okay, so what does all this mean? What does all this data mean? Well, one thing is, for some users, the Anycast site that they're getting seems to be fairly sticky. And those people under attack, when a site is under attack and overwhelmed, are going to lose service. Other cases, users are going to shift to other sites and maybe get better service, or maybe get only slightly better service. And exactly what happens to you as a user is largely out of your control. It's a function of what choices the operators make. It's a function of the particular configurations of routing at these sites, and it's a function of the traffic at these sites and how it interacts with DNS and BGP. So I think we have to think about what these implications are and how we convey them to users who in the event of these, for what they should expect when sites are under stress or services are under stress. So the final thing I want to talk a little bit about what should happen, or maybe the right word is what could happen. What choices would we make if we had infinite amounts of information? And so I want to run through a thought experiment to think about a fictitious service with 3 sites, one of which is larger than the others, and think about attackers dumping traffic on them. And so let's think about what kind of options we would like to take when we have different size attacks. So the first attack I want to think about is what happens if the attacker, those red boxes at the top, are hitting the same target, and if there's not enough traffic to overwhelm the site, in other words, if the attack traffic is less than the capacity of that site, the right decision is do nothing, right? You're absorbing the attack. That's great. On the other hand, when the attack grows over the capacity of that site, you really want to try to shed load. You want to try to shift load to other Anycast sites. And you could do that by explicitly manipulating routing tables. On the other hand, if each individual traffic from each ISP hitting a site exceeds that site, maybe, and if you happen to have a really large site, maybe you want to actually take away all your sites and just send them to the large site. If you can absorb all that traffic, that might be your best choice. And this is very counterintuitive, right? When under attack, you don't want to withdraw service, right? Well, maybe you do if you're withdrawing service from sites that otherwise would be unable to serve their customers. Except the challenge is, if the attack gets so large, it would even overwhelm your large site, then somebody's got to lose. And your best choice is to let those customers suffer because you're protecting your other customers. And that's a reasonable choice to make under these situations. And so each operator will have to make their choices, and that's a difficult choice to make depending on your architecture and what information you have. And it's always fun when you're under attack and don't really know what's going on necessarily. But I think it's important to think through what choices you would like to make ahead of time, and hopefully this kind of thought experiment gives some framework to discuss that. And then the other thing I hope to take away is what information, to ask oneself, what information would one like to make good choices under stress, to make the right choices? And I think that's an open question. I haven't heard a lot of discussion about that. Okay, so what should you do right now? I think right now, it's a complicated question, but depending on the kind of information you have, I think there's something to be said for being careful about what changes you make. And I think it's a really important question to understand what changes in the future we'd like to make so we can get better service when under stress. So just one quick aside at the end, this is in the paper as well, we do see some evidence of collateral damage when you have such large amounts of traffic coming in to given data centers that might be shared by multiple people. You can actually see pain on services that weren't directly attacked. And we know this has happened before in other cases of large denial of service. It's just something to think about here as well. So the recommendations, I think you have to be careful here. But longer term, I think there's an important need to better understand these conditions and to talk about responses to denial of service because they don't seem to be going away. Earlier we talked about Anycast sites and how many you need for latency. I think it's clear a very big motivation for having lots of Anycast sites is to get lots of capacity, and that's important. A challenge from this talk is even just having lots of sites is not necessarily enough if those sites get overwhelmed and those customers suffer. So maybe we could do better there. Anyway, so I think there's important to consider more study here, and there's data and paper available below, and we have this very nice illustration from our colleagues at Holland who gave a version of this talk at Holland Fights Back last week. So anyway, any questions? Coffee.
Very cold.
Hey John, it's John Kristoff at DePaul University. This is a very interesting talk, very well done. So I assume most of the time, most Anycast operators are advertising prefixes from their Anycast node to peers and upstreams, and at some point they're in a situation under duress, and if enough so that then that route announcement goes away and traffic flips. So my question is, maybe to you or to the group, is does anyone do routing a little bit differently so that the route is more or less nailed up or comes from a different place so that routing that won't be withdrawn or it won't bounce, so traffic will flip back and forth?
Yeah, so other people in the room may want to comment on that. And the public data that we analyzed here can't answer that question directly. We just saw the outcome. I do think it's highly probable that some of routes were withdrawn because of BGP failures due to traffic overload, as you suggest. I think it's also probable that people were making operational changes to try to manage the thing. And I think, and I would expect that people are able to nail up routes that are able to survive regardless of the amount of traffic that a site gets as well. So I think you're right to push on that issue. I think the details of that are something that individual operators will have to answer. So, question?
Yes, my name is Stefan Lagerholm from Microsoft, and first of all, thank you. A great talk, and this is something that keeps me up at night for sure.
You're not the only one.
Yeah, so on page 27, you talked about just moving part of the traffic to another Anycast node there, and that would be a little bit complicated, right? Because you would have to, on the peering points, like adjust your BGP and stuff, right? So just wanted to say that another way of doing it is that if you have two addresses, you have NS1 and NS2 going to the same clusters, and then if you're under attack and you want to move some traffic, even move some of the attack traffic to another site, you can do that by just withdrawing perhaps NS2 and NS1 you're keeping there. And that's something that I think could be useful. Like sometimes attacks are very localized in Asia, for example. And to be able to double your capacity by just withdrawing NS2 and push that to another site nearby, then you can spread out on two clusters as opposed to just one. Yeah. And that's something that can be done just by the DNS people, right? Because we don't have to talk to anybody within networking to be able to do that. We can just stop the health records for NS2 and automatically BGP will stop advertising.
So that's a great comment, and I'm actually very happy that Microsoft has published papers on FastRoute and some of their strategies for managing a CDN that uses Anycast, and that's been very informative. So For the root letters, though, each letter has one IP address. That's the definition of a letter.
Right.
So
right.
if your options are withdraw your IP address, that's not very attractive for a root letter. So
Right.
unfortunately, when you're running DNS, you don't have that choice.
Right, and that's why I don't see this, perhaps, I don't see how you can do this quickly and easily on a root server.
So one would assume that if you're running an Anycast and talking to your upstream ISP, you would have some interaction with them and maybe some way to influence the particular routes that they announce upstream. So I think you're absolutely right. It is difficult to do this. I don't think it's impossible. So,
thank you.
This is Andre Seasoning again. This is just an idea that popped in my head. Have you thought about using remotely triggered black hole filtering to help the Anycast nodes under attack?
I'm sorry, I missed the word at the beginning. What was before black hole?
Remotely triggered black hole filtering. Basically, you send a route that your peer should just dump the packets to. So if it might help.
So should we just black hole certain source addresses? Yeah,
basically.
Yeah, that'd be a nice thing to do. Sorry about your Internet of Thing device that's attacking me. Maybe it's kind of a shame if I have to black hole Comcast. So it's hard to black hole is what I'm trying to say when the attacks are widely dispersed and you don't know who's, and the attacks are all spoofed. Anyway.
Hey, this is Marek from Cloudflare. I just had a quick question. You mentioned 5, was it millions of packets per second and 3.5 gigabits per letter. I was interested if you have any statistics into how this is distributed over sites. Like, is this the London site taking 3.5 gigabits per second, or is it all sites combined? Or?
Yeah, so that's a great question. So the data that we have from IPATLAS can't answer that question. You'd have to talk to operators. So I'm sorry, that's not, to the best of my knowledge, publicly available.
All right, thanks.
Hi, John. It's Joe here again. So you mentioned that every root letter has a single address. And I think it's probably still true, I haven't checked recently, that some still do only have a single address, but most have at least 2, right? Because you could segregate V4 and V6 traffic if you wanted to between different places and segregate the attacks on each protocol. It's also the case in each address family that some, at least several, root server operators have multiple prefixes overlapping the single address that they serve. So that, for example, they could withdraw a more specific prefix and allow traffic to reroute to SOCA sites. So you might want to, might be worth going through the data and seeing whether any of those effects correspond to some of the rerouting that you saw. I think those kinds of active mitigations from the operators are a little bit more likely than BGP going down because of traffic.
That's a good point. So we did not, we counted BGP operations. We did not try to dig into them, and it would be very interesting to see if we could tell more about what actually happened.
Yeah, I'm not sure that anybody's doing that kind of active mitigation with different size prefixes, because originally this was, it was a workaround for a bad idea that I once had in an ISC document about no export, and Randy Bush once pointed out loudly at a microphone how bad that was in some cases. So there was a mitigation that involved like a /23 advertised in parallel with the /24, with one having no export and one not, and a corresponding with 47s and 48s for V6. But I mean, it'd be the kind of thing you could do here.
You know a lot more about routing than I do. So yes, we should, I mean, those are good things to look at. And in fact, the other insight you had about, gee, we do have 2 IP addresses, V4 and V6. Yeah, we could protect our V6 customers, all of them.
Okay, let's take one last question before lunch.
Sorry. One last question. I'm Gustavo from Domain Tools. You were talking about withdrawing, but there's another option in BGP, which is to make yourself further away by putting more hops in your path. And if you take that strategy, you would push the data out, or push the attack back into the network in a certain way. Is that not a good solution?
Sure. When I said withdrawing, I meant doing something that causes some of the traffic to go somewhere else. I did not mean specifically the BGP withdraw message. So, yes, and there's a bunch of clever tricks you could do, absolutely, and they're well worth exploring. Thank you.
Okay, thank you very much, John.
Thank you.
Thank you. Okay, the lunch arrangements are similar to yesterday. Lunch is being served in the Oak Room, which is the first room on the left down this corridor behind us. You will need your badges to get in for lunch. As with yesterday again, the food on the lower shelves are for those who have pre-specified dietary requirements. There's a mixture of meat and non-meat foods on the upper shelf. So, question?
Yep, just very quick reminder, there's a PGP key signing which will be in here at 1 o'clock, so bring ID and a pen.
Yeah, and this room is obviously not going to be locked, but nor is it necessarily going to be attended apart from that, so please take your valuables with you.